Please start.
Change the slides. Okay. Ladies and gentlemen, it is my privilege to introduce Dr. Anand. He joins us today as a distinguished resource person for our workshop on contemporary image processing and cybersecurity applications. Dr. Anand is an education success engineer at MathWorks. He works with different institutes and educators across India to support them in their curriculum and research activities. Prior to joining MathWorks, he did his PhD in the topic of neuromorphic computing applications from IIT Kharagpur. MTech in VLSI Design and Embedded Systems from NIT Rourkela, BTech in ECE from Techno India College of Technology. He has authored and co-authored more than 15 research articles in journals and conferences. His area of interest revolves around digital VLSI and artificial intelligence applications. Please join me in welcoming Dr. Anand. We are privileged to have him here today to share his expertise and insights with us. Sir, Dr. Anand, sir, please continue. Sir.
Thank you, Dr. Santosh. Thank you very much for the warm welcome and for the invitation to this FTP. Let me...
Sir, you can share your slides also, sir.
Yes. Now you are co-host, you can share your screen.
I can share my slide, yeah.
Yeah.
Let me share the screen. That will be better. Is my screen visible?
Yes, sir, visible.
All right. So also see around 15 participants here. So there is a chat window also. So while I'm presenting, if you have any questions related to the presentation, related to the topic, feel free to drop it in the chat. At the end also, we will have some time for question and answer. And in between also, if you are missing some points, you can always raise your hand and let me know so that I can repeat what I'm talking about. So let me now close this chat window, and yeah, so just to tell a couple of more lines about what we do in the education team at MathWorks. So we work with educators across different institutes to help them. So by helping them, it means we try to make their job easy by supporting in their daily activities. So if they are teaching any courses, then how we can aid them by assisting some MATLAB related scripts which could be used as a part of the course. So that becomes help in the teaching side. Or if they are doing some projects which might require some workflows, so we can have a discussion with them and let them know about that. So that is one part of our role in the education team. So any of you after this presentation also, if you are interested to use MATLAB in your teaching research activities, feel free to get in touch with our team. Anish is also here. So he will be the first point of contact. He's the account manager, and I will be in the addressing you from the technical side. Now coming to today's talk on tutorial on interoperability between MATLAB and Python. So I've chose this topic because I saw the FDP is on contemporary image processing and cybersecurity application, which is two emerging trends. So out of the two, I chose the first one, and inside the first one also, this is a very subset of that. So by contemporary image processing, it's like it's unlike the conventional image processing methods. So there has been a lot of research, a lot of books related to image processing, how people can analyze image, get features out of it. There are many techniques on that. But then in the last decade or so, we have seen the evolution of AI models, especially like I can say CNNs, like convolutional neural networks, which are good for processing images. So taking that into consideration, and from the tool perspective also, so you can see there are two tools mentioned here, MATLAB and Python. So there are various tools where we can people usually work for different tasks. So each tool will have some benefit over the other. How we can leverage both of that. So that's why this tutorial on how we can interoperate between MATLAB and Python comes into the picture. And through this tutorial, I will go through some examples. I will show you some examples, and I will also talk about some use cases which will be useful for your work. And that's the idea. Now, talking about the platform MATLAB and Simulink. So, how many of you have used MATLAB and Simulink before? If you can just mention it in the chat, I will just have a look at that. You can type a yes if you have used both MATLAB and Simulink, or you can add something more also into it if you want. So I have not used. I have one comment. Okay. Okay. Fair enough. Only MATLAB. Yeah, that's a good answer. Only MATLAB. Anyone who has used Simulink? So I got two answers. One is new. They have not used MATLAB and Simulink. Annie has mentioned that. Jilna has mentioned that she has used MATLAB. Priya has mentioned she has used MATLAB. Okay. In case anyone has used Simulink, you can also mention that. So that will be a have used MATLAB for image processing. Yeah, thank you. That's a good answer. So MATLAB for a specific domain, image processing. So MATLAB is good for image processing tasks. So you have used it. Thank you. So I have some idea about the audience now. So I guess Simulink users are not many, or maybe no one has used Simulink till now. And we have some users who have used MATLAB for image processing or for some other cases. And there are few who have not used this at all. So what is MATLAB? MATLAB is matrix laboratory, and it is a computational tool which was founded long back in 1984 by Cleve Molar. So as a part of his PhD work, came up with some coding which eventually helped in forming the company. So it is very good at matrix computations, and now after so many years it has evolved to much more. So it's a numerical computing environment, okay, especially designed for the engineer scientists so that they can apply different technologies. They can use it to achieve many things in many different areas. Okay. So and what is Simulink? Simulink is just an addition to MATLAB. It's a part of MATLAB which provides you the graphical environment. So this is it provides you the graphical environment where you can make your systems using blocks inside the library. So there are multiple blocks inside the library, and it can help you to do dynamic simulations. So there are solvers behind this platform which can help you to do these simulations. And once you design your system, you simulate them, then you can test the systems prior to code generation and deployment. So with this platform, it is heavily used by the industries, especially the automotive industries or the aerospace industries, where they have to design a lot of automatic components, let it be control systems and so on. And once they make that system, prior to deployment, they go through a lot of verification or industry standard checks. So that's where this platform is used. So MATLAB and Simulink, they are the two flagship tools by our company MathWorks. And in addition to that, there are toolboxes. So there are like 100 plus add-on toolboxes. Okay, so more than or close to 130 toolboxes catering to different domains. So for example, Renji mentioned that I've used MATLAB for image processing. So like that, if somebody is using MATLAB for control system, or somebody is using MATLAB for communications, for signal processing, and so on for automotive. So there are different areas which have specialized functionalities, specialized apps. So those features, functionalities can be used to address that problem, that application. And it's a very basic tool, getting started tool. So if I just talk about myself, I was introduced to MATLAB when I was in third year of my BTech program in a course called DSP. So in that course, we understood how to compute matrix, and later we also understood how to design filters using the MATLAB interface. I had no idea about Simulink. Simulink was, I saw some of my students during MTech who are doing projects related to controls were using the Simulink platform, where I was all doing a MATLAB-based coding to model some device-related characteristics. Okay, and uh, that way I used MATLAB. And after joining the companies, I've been in the team for around 3.5 years, and I've learned a lot more. And it's like an ocean. There are so many things, but the idea is you need to understand which are the things you will require for your work, whether you're teaching work or research work, and how you can make use of it the best. So this is a big brief background about MATLAB Simulink. And now coming to the agenda of today. So there are four things which I will cover. So one is about what are interactive notebooks and apps in MATLAB. So what are uh, live scripts? So a normal MATLAB file is a .m file, but what are live script, the .mlx file? What are the capabilities of live script? What we can do with that? I will go through that. Then the main highlight will be working together with MATLAB and Python. So this is the main topic where I will spend most of the time. And also I will discuss a few ways how you can optimize the MLDL models. And along with that, I will discuss some use cases in industries, how industries are leveraging these interoperability workflows. And finally, some upskilling resources so that you can get started after the webinar as well. So coming to this page, so you see interoperability has an impact across different vertical applications. So on the left, you see it is related to the automated driving scenario, where we need to detect objects and recognize objects. So whether we need to detect the lane. So whenever a car is moving, there are two things in front of it, the path and the obstacles or the vehicles. So we need to detect the lane as well as the vehicles, which can help the control system decide how the car should move next, what should be the speed, what should be the turn, and all those commands. And if somebody has to do this automatically without a driver, then we need some system which can help us process these data. So these data means the video data. Some camera is capturing real-time video, and that video will have a lot of image frames, and those frames needs to be processed by some model and within a specific amount of time, so that we can take the decisions. So it's a very complex, not a very easy task. Very few companies uh, uh, are leading in this front. Some have achieved, like Tesla and so on, they have achieved a lot. So what are the complexities involved? So one thing is very obvious here. So it's using large AI models to help us predict these things. And when we are talking about large AI models, it is using a lot of data also. So a lot of data collection from different scenes is needed. So here you see detectors are often models imported from the OSS deep learning frameworks. So OSS, the open source platform, there are many deep learning frameworks which might be available. So these are very helpful. So these can be used for these models can be used. These models can be imported. However, why are we importing the model? The question comes into picture. So the Simulink platform, which I was talking about, so it is very strong in these MBD workflows or controller design and verification. Okay, verification, validation, testing. So all these things, it is very strong. And this AI component becomes a small part of the entire system, okay, where it is trying to do some kind of prediction. So if we are able to import these models which are there and use it in the system as a whole, then the entire system would be simulated, which will help us in the final step before deployment, the code generation and testing. So that's the idea here. So these industries, in case of automotive, they are very strong users of this Simulink platform where they make their entire system and do a lot of analysis before deploying it into the hardware. And when AI comes into the picture, whether it's processing of video stream images, that becomes a part of the system. So that's how you interoperate. Similarly, in another application, if it's related to audio signal processing, so calling data processing in MATLAB from Python becomes another scenario. So MATLAB is a very good place where you can process data. There are many facilities to uh, do this data pre-processing. So if somebody is working on Python and they want to use some MATLAB functionalities, they can call the MATLAB function, MATLAB apps like that into the Python framework. And I will show that in one of the demo also today, how you can do that, calling MATLAB functionalities from Python framework and utilize both of them. Then in this slide, we see some examples of interoperability in the industries, like Bosch designs and implements LiDAR point cloud classifier with MATLAB and deep learning toolbox. Mercedes-Benz simulates hardware sensors with deep neural networks. So here you see the workflow for the Mercedes, for instance. So the first part, the training part, has been done in Python framework. And when they are doing the transfer learning, so they are using it in the MATLAB window. So they are using the deep learning toolbox, they are using the fixed point designer, and then they are targeting it to the hardware. So the thing that I mentioned, so that is the workflow we have seen. Company like Mercedes-Benz use that to leverage both of them. And then there are more stories apart from automated or auto industries related to automobile. We have chemical industries where they deploy AI and automation systems with TensorFlow and MATLAB. So they also leverage both the things. So whenever they get something available in some platform and some other features like the data processing in MATLAB, how to combine both of them, or automating genotoxicity assays with imaging flow, phytometry, and deep learning. So how they are working on these assays, so related to some biomedical, biotechnology related works industry. Now, for us, when we talk about the roles that we play, so either we are an engineer or somebody is a programmer, somebody is a student. So what are our common requirements? Okay. So an engineer may ask, like, I would like to integrate my colleagues' Python codes in my MATLAB simulation models. So is it possible? Okay, that might be a question. So there are a group of engineers who are collaborating on a project, and somebody is using Python code, somebody is working on MATLAB, and the question is very simple. If we are collaborating, can we use the Python codes in MATLAB simulation models? And the answer here is, of course, you can call Python code directly from MATLAB. So this facility was not there before, but because of the need from the users' feedback, our development team have worked on this aspect, and they have made this possible. So if somebody wants to call a Python code directly from MATLAB, that is possible. Then the next question from a programmer. So can I use my colleagues' MATLAB codes and apps in Python? So a programmer might be comfortable in their programming environment like Python, okay, but they want to use some of the functionalities of their colleagues who have worked in MATLAB in the Python framework. So can they do that? And the answer to this is yes, you can call MATLAB functions and apps directly from Python. So that is also possible. So if you're working on Python and you want to use certain functionalities of MATLAB, so through a MATLAB engine, you can call those things. Then for a student who are working on different projects, maybe from using different hardwares as well, may have a question, can I build an engineering project using Python AI algorithm and deploy it to hardware? So the answer again is yes, you can. So you can import the Python model into MATLAB and Simulink and then deploy it to hardware using the automated code generation. So there are two steps here. So they can import the Python model, then they can convert it to the MATLAB equivalent, use it in the Simulink environment, and try to use the code generation facility to target into hardware. So that's the workflow which the industry people also like the Mercedes-Benz have followed. So that is possible. So these are the common requirements of an engineer or a programmer or student, and these things are possible, and we will see some of that. Now coming to the question of what is interoperability. So we are talking about interoperability, but what actually are we doing when we are talking about these two different frameworks? So on the left, you see we have MATLAB and Python logo. So, and on the right, we see there are different frameworks. So can anyone guess what is happening here? So, or what is interoperability? What do you understand? What is your understanding of interoperability? In one or two words or one or two lines, you can unmute yourself and tell. If you're able to unmute yourself and tell, that will be better, or you can use the chat window. So what is your understanding of interoperability? There are no right or wrong answers, means whatever you are thinking, if you can let me know, that will be nice of you. I see no answers. Okay, so no problem. Let me tell you what we mean by interoperability. So there are mainly two things. So one is the co-execution part. So when we are working in MATLAB, whether we can use Python codes from there, or when we are using Python, whether we can use MATLAB functionalities from there. That is the co-execution part. And the second, on the right side, you see, so these are models. So like PyTorch model, TensorFlow model, ONNX is Open Neural Network Exchange models, other frameworks. Okay, so other frameworks models can be converted to ONNX and it can be imported into MATLAB. PyTorch TensorFlow can be directly imported to MATLAB. So this importing of models is, or model exchange, you can say. We are exchanging the models from one framework to other, is another capability. So these are the two main capabilities when we are talking about interoperability. So you see here, so First is the MATLAB Python co-execution, and the second is model exchange, where we are yeah, I see one comment using MATLAB codes in Python and Python codes in MATLAB. Absolutely correct. So that is what we call as MATLAB Python co-execution. So that is definitely a right answer. And the second one is more specific to AI, because when we are talking about these models in ONNX, PyTorch, or TensorFlow, these are basically the AI models. So when we are exchanging those models and using it in different frameworks for our tasks, so that falls in the model exchange category. Okay. Now today we will go through two demos and we will try to see both of these things happening. So how we can do co-execution, how we can do model exchange, okay, and so on. Now before going there, one thing to mention. So there are resources available online, like there is a using MATLAB with Python page which mentions what are the things you need to consider when you are calling MATLAB from Python. So for example, one of the important thing to consider is to use this MATLAB engine API for Python. So you need to install a MATLAB engine API for Python, okay, which will help to make the connection between Python and the MATLAB interface so that you can call those functionalities. Okay, so these things are there. And then coming to the next slide on evolution of deep learning in MATLAB. So this is a slide from 2016 to 2021. And you see in 2016, there were features added pertaining to CNNs, the convolutional neural networks, good for image processing tasks. And some pre-trained models were added. A cafe importer facility was there. Then in 17, the toolbox name was changed from neural network to deep learning toolbox. So why? Because earlier we had capabilities for shallow neural networks where we have one layer of one hidden layer with an input and output layer. And these are the basic units to form a deep learning network. And when we are introducing CNNs, which will always have some components of those shallow or fully connected networks in addition to other components. So we are including more models there. So that's why the network or the toolbox name was changed there. And some more algorithms pertaining to time series data like LSTMs and other things were added. Code generation facilities were added. And on the interoperability for front, TensorFlow Keras importer was also there. Then in 18, there was an app introduced, a dedicated app known as Deep Network Designer. So Deep Network Designer is the app which is used to model or used to design those deep neural networks, and we can do training, and we can also use pre-trained network from there. So this is one app which was used. Then in 19, there were few more things you see with respect to explainable AI, certain concepts which are helpful to understand, like occlusion or GradCam, to understand how which part of the image is helping us to determine the correct prediction. So those things were added. And 2020, more things were added. 2021, we see there are around 250 plus examples, around 250 plus examples on different areas, which has an AI component into it. Different application areas were added, so that can be a starting point for people to work on. Then in the next slide, there is some more things mentioned in terms of the features which are added. And if you see 2022 and 2023, over 500 plus examples were added. So now, in addition to the capabilities pertaining to interoperability, code generation, other things, examples were also increased almost 2 times from what we saw earlier in 2021. So this is because these examples become a good starting point for different people working in different applications who may not be mm, uh, who may not be very comfortable to start something from scratch. Okay, so these examples give a head start. So this gives us a base to get started, and then you can use that to modify for your projects. So that was the idea for adding more examples pertaining to this. Then in the next slide, we show this Gartner's Magic Quadrant for 2021 for data science and machine learning platform. So here we see MathWorks is in the leaders quadrant in addition to some other companies. So this is because our tools empower the team, those have limited AI or data science experience. So we can apply the complete workflow for data preparation, AI modeling, system design, and production code generation, and deploying AI models on these embedded devices, edge or enterprise systems is possible, and tackling integration challenges and to reduce the risk of designing AI-driven systems with Simulink. So these are couple of or 4 points which is mentioned, uh, which is because with the reason why MathWorks is in the leaders quadrant in this sector of data science machine learning platform. Now coming to the topic of what is AI. So why AI? AI is artificial intelligence. It's the ability of a computer to perform tasks commonly associated with intelligent beings, like learning or problem solving. So it's the superset of ML and DL, and ML is just a subset of AI uh, when we are not writing some rule-based or hand-based coding, okay, to make them algorithm. Rather, we are using data. We are learning a task from data uh, that falls into the machine learning bucket, and there are different machine learning algorithms for that. And deep learning is again a subset of machine learning, which is again doing the same things. The only addition here is these networks are more complex, and because they are complex, they can learn from raw data. So we may not have to do a lot of pre-processing or extract some features, do some feature extraction. We can use the raw data in those complex networks, and because these are complex network, it will also need a lot of compute power. So this is the main idea of AI ML DL. And when we go further and talk about the types of machine learning, so there are two types of machine learning. One falls into the supervised learning category, and the other falls in the unsupervised learning category. So when we talk about supervised learning category, it means we not only have the data with us, but we have the labels for the data, or the output uh, termed as the output data, or the ground truth of the data. Okay, so that is supervised learning. And when we are talking about unsupervised learning, we only have the input data. So inside supervised learning, there are two categories. So one is regression. Okay, so on the right you can see a load forecast system where we are trying to predict the load uh, or the load needed for a particular scenario based on the past data. So it's a continuous time value that we are predicting that falls under the regression category. When we talk about classification, we are just trying to classify some categories. So for example, if we are doing a human activity recognition, so collecting data from your mobile phone with accelerometer, gyroscope, sensors, and we need to do 5 types of classification, whether a person is standing or climbing upstairs or walking or sitting or sleeping. So that falls into the classification category. Similarly, when we are talking about unsupervised clustering or unsupervised learning, so it's basically we do not have any labels with us. So we need to do some statistical analysis, some statistical methods which can find some common characteristics from the data and separate them. On the right, you see it is color coded. So 5 different clusters are there, which are color coded with different categories. And it's nothing but relation between the vehicle speed and the engine speed. Okay, when the gear selection is changed from 1 to 5. So based on the gear selection, we have a higher vehicle speed. So that's how we can understand the data. But when we do the clustering algorithms, in this case, we get these this kind of idea with us. Okay, so now here you can see some more examples of the models for each type of machine learning. And this is not an exhaustive list. So for example, for regression models, we have support vector machines. We have naive Bayes. For classification, we have linear regression, ensemble method, decision trees. For clustering, we have k-means clustering, hierarchical clustering, hidden Markov model, and so on. And for all of them, we have neural networks. The neural network are very powerful models which can fit and address all the categories of algorithm. And these are the fundamental blocks of deep learning. There is another branch of machine learning, which is reinforcement learning. So here we don't use that much of data. There is a different way this learning mechanism happens. So currently we won't talk much on this aspect, but there is a 1 hour on-ramp course in our MATLAB Academy website. So people who are interested in reinforcement learning, especially people who work on robotics controls related applications. So this becomes a good emerging idea to use there. You can look over that. Now coming to the next slide about the data types. So this FDP is about images. So we will focus on the images part, but it is very important to understand what kind of data you are working on when you are working on any problems related to ML or DL. It can be an image, it can be a signal, it can be numeric, it can be text. So depending on the type of data, we will need to identify what kind of models or networks are preferred. So and that becomes one of the criteria to select the models. Secondly, what kind of pre-processing or you need to do on the data. So if you need to extract certain features or some useful information, either from the image or the signal or the numeric data, so that becomes a data analysis or data analytics kind of thing, because the model won't understand what you feed to the model unless there is a human intervention. So the human who is working on the application will have the best idea about what is the useful information which, if I feed to the model, can give us a better response. So uh, if we give some unnecessary data, for example, in this case, if you are seeing numeric data where we have a age category, a weight Q category, a group count, mean blood pressure, something related to health, and suppose there is another column named as serial number, which has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and if we feed all the columns together with the serial number, then that becomes bad data or data which is not required. The model will get confused because model will try to fit that column as well as one of the important features. So whichever data which is actually causing an influence, which is influencing to the result of the outcome or the prediction, should be identified, should be sent to the model, and anything which is not required uh, can be filtered out. So if we talk about signals, so commonly we can have a noise component in the signal when we are capturing through sensors, and in cases this noise will be an irrelevant thing. So maybe filtering out the noise can be one idea, and then taking out the useful information using statistics can be a good way. In images, again, there are conventional image processing algorithms. So if you're using machine learning techniques, so maybe you need to understand those in image processing algorithms. So let it be like HOG, HOG, a histogram of oriented gradients. So it's a very good feature for getting the gradients out of the image for uh, face classification or uh, human face recognition, those kind of activities, or that if you have to detect edge colors, those kind of features can be another thing when you're dealing with machine learning problems. When you're dealing with deep learning problems, you can use the image as a entire raw data set. So these are few things which is very important. And now coming to the other steps. So data preparation becomes the first step which we were discussing. So cleaning the data, preparing the data, adding the human insights in the data. And sometimes it can be simulation of the generated data, okay, or simulating generated data. So if the amount of data set is less and you are using some deep learning models, so there may be scenarios it may not work well. So you need to simulate or add synthetic data. So that is another thing to be considered in the data preparation step. Then in the AI modeling step, you are using the data to model or create your model, fine tune it. So you can use hardware accelerators for increasing the speed. You can here is the place where you do the interoperability also if you are using different frameworks. Once that is done, the third step is to integrate the AI model with the complex systems and do the system simulations, do the system verification and validation. And then comes the final step of deploying one second. So then come the deployment step, and these 4 steps are the ones where we need a lot of iterations and refinement also. So if we are not getting the desired result at the end, so we need to understand where we can improve. So we can improve either on the data preparation step, or the AI modeling step, or the simulation and test step, or the deployment step. Okay. So now we will see an example for the co-execution part. Okay, so this is a Boston housing data set. So Boston housing data set is a very commonly used data set in machine learning, where we are predicting the house price in the Boston area depending on various features, maybe the size of the house, the location of the house, and so on. So this prediction of the house cost, how we can do it, we will see that. So one second. So I am opening a Jupyter notebook. Okay, so in the Jupyter notebook, go to the Python folder, and here I create Python file. Okay, so first of all, let me add couple of sections out here. Right, we need to start a MATLAB engine out here. So this is the very first step. So you need to import the MATLAB engine to the Jupyter notebook, and you need to store it as an object. So matlab.engine.start_MATLAB. So now this is stored as an object in the variable m. So this is the first step. Then suppose what we will do is that we will call a built-in MATLAB function. Then we will try to call a custom MATLAB function. Then we will try to call a MATLAB app. Okay. Okay, so these are the three things we will do. So when we call a MATLAB function, so there is this function known as magic. Okay, so if we anybody knows what is a magic function in MATLAB? So this magic function, if you provide a dimension of 3, then it will create a 3x3 matrix for you. And if you take the sum of any row, addition of any row, column, diagonal, it will be the same. All right. So when we do this magic 3, and if I execute this function, I need to add this m dot here. Okay, I need to add this object so that it can access the magic function. So if I don't add this function and execute this, I get an error. Okay, it is not able to identify this functionality. But once I do this, you can see the result. So here is the 3x3 matrix, which is there. Secondly, now if we want to call a custom MATLAB function, so let me show you the custom function out here in MATLAB. So this is the custom function. There is a function in tri area, which is taking the base and height of a triangle, and half into base into height is the area. We're returning it back to this area function. So this is not a inbuilt function like magic, but a user-defined function. So if we want to access that function, again, we can check that. We can write base, we can define a height, and we can store the variable into this try area function. And we can print the area. So is the line of code okay? If I execute this, will it work or not? What do you think? I've defined the base, height, I've called the function, send the base and height as argument, storing the area and printing it here. Is it good, or do I need to add anything? You can use the chat window. I'm having a look. M dot, yeah, thank you. So that's absolutely correct. So I have not used the M dot. So whenever I am accessing any function, whether it's a built-in function or a custom function, I need to use this M dot operator. If I don't use this M dot operator, so here there is an error. It is not able to identify the try area function. But now with the M dot operator, we can compute the area. Okay. Now the third part. Okay, we have seen the custom function. We have seen a built-in function. Now if we want to call a MATLAB app to do some functionality. So this is where we will work on that Boston housing data set. So we will be accessing the data first. So let me use some commands to do that. So here we are accessing the Boston dataset from sklearn.dataset, which is a popular platform for storing dataset. And then we are printing the size of the dataset, like there are 506 rows, 13 columns pertaining to the features and maybe the final price of the data. Then after loading the dataset, what's the next step that we should do? So whenever we have a dataset, we need to pre-process the data. So in this case, we are pre-processing the data into a MATLAB double format, okay, so that the MATLAB app can understand. Okay, when we are going to use a MATLAB app, it should understand the type of data. The MATLAB usually the default nature of the variables is in double format. So we are converting the X and Y variables into double format, and that's the pre-processing we do. And then we have to load the data to some app. So the app name is regression learner. So this is a regression problem, a supervised problem in the form of regression. We are trying to predict the continuous time value of the house price. So we just use the m.object with the regression learner app, and we also feed the X and Y variables, okay, to the data set. And this should invoke this app in the MATLAB window. So here, so there is a separate dialog box, GUI interface for regression learner, which has opened up. And here, the data set, you can see there is 506,13, and the response of the data set in the variable y is all loaded here. So either we can set some data for testing, maybe 10% of the data, or if we have something separate, we can leave that out. So let me start the session for this. And by default, you see there is one machine learning model named tree loaded here. But what I will do is that instead I will show you. So there are so many different models out here. So if you are not sure about which model will work best on your data, so you have to do some literature survey to figure that out. But before that, you can either go all quick to train or maybe all models in this case. So it's not a very big data set. So I choose all the models, and I'm deleting tree model. So all the multiple models are loaded here, and I'm clicking on this one button to train these data sets. Okay, so you see the training has started, and depending on the number of cores the use parallel will train 4 models parallelly, 4 cores, and that's how it will try to train like 28 models. So you see there are 28 different models on which the data is getting trained, and once the training is completed, you will get a metric. Root means square error, the validation metric, and the metric which is having the lowest value will be like the best model out of the lot. So very quickly you can get the results for 28 different models. So if you have to do the same thing via a coding interface, so even if for one model you need maybe 3, 4, or 5 lines of code, so for 20 models you will require 5 into 20 lines of code. Okay, so you have to write it, write those things. So this application is helping you to do all those things very quickly. And let us see which one is. So this one is the best till now. I'm clicking on 2.18. And while the others get trained, let me show you this results table. Okay, so when this is selected, you can also see the other metrics related to the model. And currently we haven't done any optimization, but if you need to do optimization, then you can go to the optimizer options, and there are optimizable version of each of the things. So here you can enter and do those optimization as well. Okay, so for this case, optimizable GPR. So in the results table, you can get a comparison of all the models which is trained, so which is a good thing. You can export the results table into workspace, export the result table to file, okay, which could be a good way of analyzing between different models as well. Two 2.21. So this is the lowest one. So let me select this one. So here is the response plot between the true and predicted ones in colors, and the error can be also plotted, the distance between the true and predicted. There are other ways to also visualize your result in terms of the predicted response versus true response. So how much it is deviating from the diagonal. So that will give you the idea. The perfect prediction is along the diagonal. So whichever is closest is a better prediction. So there are very few which are away from the diagonal. And you can generate the function of this thing. So if you click on generate function, so you can see the code in the form of a function, train regression model function. Okay, taking the data and the response as the input, and all the code which is used to train that model. Next, what you can do, you can export the model. So let me export this model. And with the variable name trained model, I'm exporting this to the workspace. So the model is exported to the MATLAB workspace. Now we have trained the model. We have identified the best among the one without doing any optimization. So that is the further thing which can be done. And we have exported the trained model with us. So next, what we can do is that we can import the model itself from the workspace. So with this command, we are accessing the workspace, the trained model, and we can see what are the model contents. So it has a predict function which can help us to do the prediction. Okay. So next, what we will do is we will predict, use the predict function, and we will store it in the predict function variable, and we will test it on some data. Okay, so the X data and Y test that we have just accessed the data set which was loaded into the X and Y variable. And next we want to just plot it. So for that, we have imported some of the libraries like Seaborn, NumPy, and Pandas, and we will be using that library. Then we need to prepare the data. So we want to use the NumPy library to convert the data into array format, and we are using again the library to flatten the data, which will help us to prepare the data for the analysis part here. Similarly, the pandas library that we imported, so we are using those libraries to convert it to a data frame, a dictionary object. And then using the Seaborn library, so we are able to create a scatter plot of the same on the test data. Okay, so we use the model and we applied the test data on the predict function model, and we were able to plot it here. So this is one way of co-execution that we saw now. Now I will go back to the presentation and continue with my slides. So beyond machine learning, so here we saw mostly about the machine learning part and the co-execution, but when we are going for deep learning, the picture is very much similar. Only thing is that the deep learning will have different layers, different neural network layers associated with it. And this, in this example, you see a fully connected neural network, and also some at the very bottom you see there is an input and output image. So these are like some deep neural network which is able to identify synthetic or generate synthetic data set. Okay, so there are many capabilities of this neural network, but the main idea here is that these networks have learnable parameters like weights and biases, and the hyperparameters like learning rate, number of epochs, mini batch size. And commonly, again, they are also used for classification or regression. And they are like different blocks. So there are different networks, which are the researchers have found out, are giving performances, and those are like the standard models known as pre-trained networks. And architecture wise, when we talk about deep learning, either it falls under the recurrent neural network architecture, where it is processing time series data, or it falls under CNN architectures, which processes image data. So if we talk about a signal, time series data, and we want to use CNN for that, we need to convert that into appropriate image format. For example, spectrogram is a very, it looks like an image, but it contains the time frequency component and the energy component of the signal. So it can be converted and used in CNNs for that case. And the main thing to be understood here is that what are we doing with CNNs? So mainly because there are a lot of pre-trained models available which have been trained on large data set like ImageNet. So that is available to us. We can use that, and that becomes a very good starting point for us to do transfer learning. So if we want to do transfer learning on our own data set, we can use pre-trained models to do that. And this is the general structure of a CNN, where we are passing an image, okay, through some convolutional layers with some ReLU activation, some pooling layers, and those kind of layers are repeated. And they are helping us to extract those features automatically. And at the end, we have the classification layer consisting of those neural network. So there are different models mentioned here at the bottom right. So these are all standard model: AlexNet, SqueezeNet, ShuffleNet, GoogleNet, VGG19. So depending on the time of prediction using GPU and the accuracy that is achieved on the standard data sets, this graph has been made. So from here, you get an idea about which models would be a good idea as a starting point. Now, what we will do is that we will go to the second demo, so where we will cover the model exchange part. Okay, so we talked about model exchange. So if we have a PyTorch model, okay, which is not there with us in MATLAB, and we want to use that PyTorch model to do some image classification, for example, image captured from the webcam, then how can we do that? So we will go through that. So there are 3 stages here. So let me go to the MATLAB window. So this is a live script that I'm opening now. So I was talking about that we will cover what is live script. So basically, when you open a script file, so that's a normal .m file where you can either write your codes, m equals to 1, or write comments, or create sections like this. Okay. But inside live script, which is a .mlx file, you can write visual high text. You can write code inside this code block. So there are options to change between that. And then you can do a lot of functionalities and see the output altogether. And finally, save this, export this as a PDF, Word, LaTeX, HTML file. So these are some advantages of a live script. And in this live script, now what we will do is that we will first of all open the Deep Network Designer. Okay, so either you can go to apps, you can open this, and under machine learning and deep learning, the second app is Deep Network Designer. You can click that, or if you run this line of code, the app will be invoked. So just like we saw the regression learner app earlier, so we are opening another GUI, which is Deep Network Designer. Let me do full screen. And here you see there are options. So there are different options in the start page. For instance, so there are different options in the start page. For instance, you can import image networks. So there are a lot of pre-trained networks which I was talking about in the previous slide, like SqueezeNet, GoogleNet, ResNet 50. So these are already there. So a big bunch of pre-trained networks are there, sequence network, audio network. So either you can use these networks directly, but what if the network you want to work on is not available in this list, but it is available in some other framework like PyTorch? Then we have this additional functionality, which was again a new thing which was added. So in this case, I will show you if you are importing such networks, okay, which is outside, it's not within this, within the Deep Network Designer. We just need to import it, and here this is the .pt PyTorch network, mnasnet. I have selected that and I will import the network here. So for importing, there are these three steps. So it will first validate the PyTorch model, then it will convert the PyTorch model into a MATLAB network, and finally it will finalize the network. So in case there are some issues related to that, you will get some warning or error messages, which will help you to identify those things. So that's why these are necessary. All right, it took some more time. I think a lot of tabs are open up. That's why it took some amount of time. But like here we get one warning message. So it's just an issue. It is telling that software detected a 2D image input and automatically added an image input layer. So we need to edit the input size property of the layer before you use the network. So that's the message here. So let's go to the designer tab. And we see 153 layers are there. So you see all the layers, a very small diagram. So it's very difficult to fit 153 layers here. So let me just zoom in to see the first few layers. So yeah, so here is the input layer, and by default it has put some input image size, but depending on our task we can modify this. So in our task we are going to use the input image of size 224 cross 224 cross 3. So that is the input which will feed through this input layer. So let me either change this, or you can also drag and drop. So let me show you. On the left side you have these blocks here, like the input image layer. So if you select here, okay, and here there is no normalization done. So let me do that, because we are doing some kind of normalization using a code function. And then I can delete this, join this, maybe auto arrange. All right. Then let me export the network to the workspace. So it is exporting net underscore one, the network object, to the workspace. Okay, finally it's exported. So the network is exported to the workspace. Let me go there. So you see here we have the DL network, the DL network object inside the workspace. So now we execute the second section, basically the second line of code. It is doing is just assigning another variable named as net and copying it here. Then in the third section, we are reading an image. Using the image read function, we read a peppers.png image, and we resize the image using the IAMResize function, and using the IAMShow function, we can see the image out here. And because we didn't do any normalization, there is a function which is doing the pre-processing normalization of the image that is there. And then we convert this image to a DL array object. So this is the important step, because this DL array object format is something which MATLAB will understand, and this is the way it is done. We need to mention the dimension in this format. So once this is done, we go to the next section, and here you see we are using the SqueezeNet, which was already there. So it's another pre-trained network, but we are just using it to get the classes, because all these image networks, the CNNs, have been trained on ImageNet dataset, which has 1,000 such classes. So we can get the class names from here, and we are just you can see the value, the 1,000 cross 1 is stored in the class name category. And then once we store it, uh, we can predict the image here as bell pepper. So in the predict function, we are able to predict the image. Now what we will do is that we will try to extend this by sending images through a webcam. So let me connect the external webcam that I have, webcam list. Okay. So I have one laptop default webcam and the Logitech here. So if I use this one and if I run this code, so this took a picture and it has categorized this to a swab. So the picture was taken like this. Let me take a different picture. Maybe it was a lot of reflection. So now it has identified as a notebook. So I'm taking the picture of my laptop, the notebook. It has identified it as a notebook. So if I take a different picture out here, a monitor. So this is my external monitor in the room. So it has identified it as a monitor. Now just extending that further using a while loop so that we can do some real-time prediction of the scene. So now it is classifying this as monitor, a laptop, a projector. So this is a mobile phone. It is identifying this as an iPod. Maybe it is taking up then a seat belt, cellular phone, sunglasses, lab coat, and so on. So whatever image it is capturing, it is able to classify that. And yeah. Okay. So let me just close this one now. So very quickly, we were able to see a couple of things out here. So let me just go back to the presentation. We are close to 11:30. So let me just summarize quickly what we did. So we imported a pre-trained PyTorch model, used the deep network designer, and did some real-time image classification using webcam. So very quickly, we could do that. And there are many other things also. So in terms of applications, there are different labeler apps for signal, audio, image, video, which is helping us to do the labels for a lot of unsupervised data. There is an experiment manager which can help us to optimize or fine tune the hyperparameter. That's a separate app. The ONNX platform, we have seen some of it, how we are able to do model exchange. And then the biggest challenge is to figure out whether to use machine learning or deep learning. So it depends on a lot of parameters, mainly the dataset size, the signal domain knowledge, and the model complexity. So if you have lots of data, raw data, and you have good compute power, you can go with deep learning. But if you have good domain knowledge, you can extract useful information. And if you have less compute, you want to use less complex models, you can go with machine learning with many features like that. So the key takeaways today's session were we discussed on working together with MATLAB and Python. Especially we saw how we can do the co-execution working in Python, utilizing the MATLAB functionalities there, and also the model exchange using a PyTorch model inside MATLAB. And optimization part, I just highlighted few things like the experiment manager, and there are options to optimize to further optimize your models, which you can explore once you're ready with your first model. And we discussed about some industry use cases, especially in the automobile industry for automated driving. And we also saw a glimpse of a live script in MATLAB. So there are different links out here. AI, you can always go through the links. So you will get access to this slide deck and you can go through the links. The MATLAB Academy has different courses on different maths and different topics, which you can also look. There are engineering project ideas, student competition videos, MATLAB-based books. This is the page for the project statements. So you can assign this project to the UG final year students, team of students who can work on industry relevant problems for around 4 months. And if they submit it in the GitHub portal, they get a recognition. So there has to be a mentor faculty for that. In case you're interested, do let us know and we can talk more on this. So that was about today. So I think it is 11:31. I'm 1 minute after time. So before you go to the next session, it will just take 2 minutes for you if you can just fill this feedback form and let us know. You can just fill this feedback form and let us know how was today's session and your suggestions, which will help us to improve better. I'm also putting this feedback form in the chat window. So I've pasted the feedback form in the chat window, and you can also scan it. You can also scan it to let us know what were your key takeaways, and here are our contact also. So Anish will be the first point of contact. He's the account manager. And if you have any queries, whether it's related to licensing or whether it's any technical query, you can always reach out to us. We have an extended team who works closely with students as well, and we will get in touch with you. Also, if you have any questions, you can feel free to ask before the next session begins. So that's it from my side. Thank you, everyone.
Thank you so much, sir. Hello, sir.
Thank you, Anand.
Hello.
Thank you,
sir.
Thank you,
so
Professor
much, sir, for
Santosh. Thank you, Professor Santosh.
accepting invitation and also valuable contribution. Really, thank you, sir. And
Thank you, Professor Santosh and Silambaran. Sir?
Yeah.
Yeah, sorry for pronouncing it.
It's okay, sir.
Yeah. Silambarasan, right?
Yeah, correct.
Okay, correct.
Thank you, everyone. Thank you all for your participation. And just as Anand mentioned, please do reach out to us if you would like to learn more about or know more about these features and facilities. I will be happy to take this discussion. Thank you.
thank you, Anish, sir.
Yeah. Okay, sir. Thank you. You can stop.
Okay. So we will close the session then. But do fill this feedback form. We do have a look at this closely, and
Yeah,
this helps
sure,
us to
sir.
prepare.
Yeah, yeah. Once we collected, we'll share to you our feedback. Yes.
All right, all right. I've
Yeah,
shared
thank
this in the chat window as well.
yeah, yeah. Okay, okay. Sure. Thank you, sir.
Thank you. Thank you.
Thank you, participants. Our next session will resume at 11:45. So break. We'll again join at 11:45. Okay. Thank you. So we start.
Yes, sir. Yes, sir. You can continue, sir.
Very good morning to all. So it's my honor to introduce today's session resource person, Dr. Sumit Kumar Yadav. He is currently working as an assistant professor in CSE department at Dayananda Sagar University, Bangalore. He did his BTech in ECE specialization from Gautam Buddha Technical University, Lucknow, and did his MTech in biomedical signal processing with the ECE specialization, IIIT DM, Jabalpur. He earned his PhD degree in image processing using deep learning from the Department of Electronics Engineering of IIT Varanasi. He has more than 12 years teaching and research experience from the reputed institutes like IIT, NIT, IIITs. His research interests include video image processing, biomedical signal processing, image dashing, image denoising, and image restoration techniques. He is a member of IEEE Signal Processing Society. He has published many SCA and SCAE Q1 level research papers in reputed journals and conferences. He has been active reviewer of IEEE transactions on System Man and Cybernetics and many IEEE transaction and several leading journals of international repute. He has been received Student and Yearly Research Conference Fund of JPY 5000 in 2020 IEEE Region 10 Conference TechCon, Osaka, Japan 2020. Please join with me to welcome Dr. Sumit Kumar Yadav. Welcome you, sir. Please, over to you. Thank you.
Okay, thank you, sir.
You can share your screen, sir. Yes, sir, your screen is visible to us.
So, shall I
Please
full
move to
screen mode?
full
No?
screen mode. Yes, sir.
Okay, okay.
Yeah, please, sir. Thank you.
Okay, thank you, sir, for introducing me. And first of all, good morning to all of the faculties, all of the students, and all the employees here. So, today I would like to present a FDP cum workshop on haze preserving filter-based haze image restoration. First, I would like to introduce about myself. I am Dr. Sumit Kumar Yadav. Recently, I am assistant professor in Department of CIC AIML in Dayananda Sagar University, Bangalore, Karnataka. So, today I would like to present uh, basic introductions about how we remove the haze from the input hazy images. Actually, we will all know about the hazes are very imposed nature problems, and we will face this more difficulties in image because it is very difficult to preserve the age informations in the flat region as well as in the sharp region. So today we'll discuss about one by one how we preserve the age informations, how we remove the haze effectively from the input hazy image. So these are the contents of my presentation, in which I would like to first introduce about basic introductions of haze, then discuss some literature reviews, and there are some three works I will have actually I did work in on all the papers, and then we'll discuss conclusion and future scopes and publication as well as references right now. So so first I would like to discuss about the what is haze. Actually, haze is nothing, as I discussed about the previously, uh, because haze is nothing. It is an atmospheric phenomena in which dust, smokes, and other dry particles obscure the clarity. It is a basic definition of haze actually. So, and the main reason is that the haze is a very basic problem, and haze is an ill-posed problem. As we know that ill-posed nature problem is a random problem, so we have not a we have not a well-defined methods to remove the haze effectively. Actually, number of methods are available to remove the haze, but still we are facing more problems in removing the haze right now. So so before discussing the more about haze, first I would like to show you two hazy images. These are the two hazy images, hazy image 1 and hazy image 2. As we can see clearly from these two hazy images, some part of the images is clear very easily, but some part of the hazy images are not clear easily. So in first of the haze image as well as in second part of the haze image. So reason is that if you want to remove the haze, so we have different methods, different algorithms available, but problem is that if you want to remove the haze from the flat region, so we can remove the haze from the flat region easily, but In this sharp region, as we can see that in some buildings and some other corner parts are there where the edges are not removed easily. So we have defined some algorithms, we use some methods to remove the haze effectively. So next, in these two hazy images, these are the two haze-free images. So as we can see that this part of the haze, actually this is a flat region and this is a sharp region. Why it is called sharp region? Sharp region is means the corner of the buildings, the corner of the some uh, uh, cars, some corners of the trees also. So images or the informations which are in the sharp regions not preserved clearly actually. We can preserve age information, we can remove haze effectively from the flat region. And number of methods are available to preserve age information from the flat region. But still we are facing the problems in removing the age information from the sharp regions. And we can see easily there are the second, from the second hazy images, there are building. Okay, in this building, the corner images, actually corner edge informations are clearly visible right now. But here we cannot clearly remove the age information from this building right now. So there are still some facing some problems are available. So we have to design some algorithms, we have to implement some algorithms to remove the age from flat region as well as in the sharp region. So before going too deep in his image and algorithms in his images, so how we can represent the haze formation? So actually, we have a one equation by which we can represent our haze imaging. There is a This is the equation by which we can represent haze image, where I of x is the input hazy image and j of x is the haze free image. Actually, it is a haze free image. It is d haze image, and tx is a transmission map and A is for atmospheric map. Actually, atmospheric map is the light which we obtain from the atmosphere. If we use the if we use the artificial, if we use artificial light, then we still facing the problems in removing the haze. If we use the natural hazy images, natural lights, then artifacts and other over smoothing problems are very less compared to the artificial light. And transmission map, which we have defined, actually transmission, the lights which we transmit from the input side to our source. Actually, this is the defined actually for transmission map. So next is the basic block diagram of haze imaging model, where we can see clearly there is a one camera scene, and we want to clearly want to take pictures from the scene object. It is a scene object, and we would like to capture this image. And due to some haze effect, we face some problems in our output hazy image. So how we face the problems actually? The difference actually, the main problem is that the distance between the scene object to camera is called a depth distance. So if we have a more distance, means depth distance, then in the output of our history image, we're still facing some problems. So we have to manage our output history image by uh, fixing our depth distance. It also depends on your depth distance. If your depth distance is more, then your HP image or in the output side, we got the output haze image is mostly affected. And direct transmission, as we know that there is no haze effect, there is no atmospheric problems are available here. So we got the transmission directly right now. So there are a number of methods actually available for image dehazing, and we have to classify it into 5 categories. How we can remove the haze? The number of methods are available. So here some important classifications are we have to discuss. So first is image enhancement based method. In image enhancement based methods, we all know that some contrast enhancement based methods are available. So we apply the contrast enhancement methods and we will remove the haze effectively. There is no issue. And retinix based dehazing methods we also apply. But the reason is that we remove the haze and we got the haze free image in the output side, but it is only applicable for your flat region. Means you can able to remove the haze informations from the flat region. If you want to remove the haze from the sharp region, so these methods, these algorithms are not applicable to remove the haze from sharp vision, and still they are facing the over smoothing problems. I will discuss later how the over smoothing, um, how the over smoothing and halo artifacts are very effective in when we are preserving the age information in the sharp region. And second is a image restoration based method. As we know that image restoration based method, there are very important methods are available, like dark channel prior based methods, some multiple image based method, single image based method. In single image based methods, we use a one input hazy image, and we use this input hazy image for the haze free image. In multiple image based methods, we use some sub images of our one input hazy image, and we would like to remove the haze by using these sub images of input hazy images. For this application, we use some, as you know, that gamma correction methods. In gamma correction method, we use some gamma coefficient factors, and we have to calculate some sub images of input hazy images, and these sub hazy images we have to just fuse, and finally we got the haze free image. This method is also available, but problem is that still we are facing the age preservation in the sharp region, as well as over smoothing problems in our sharp region. Next is a fusion-based method. It is also very important, fusion-based methods, and they are very applicable. They are very good in nighttime hazy dehazing, and also very good in for single-scale haze image dehazing. But still, they are facing in a haze preservation in the sharp region. Recently, some deep learning-based methods are developed. They are very good to remove the haze information from flat region as well as sharp region. But problem is that deep learning-based methods require a very number of means resources are they required, and their computation cost is very high if we compare with the our basic methods, basic algorithms. So deep learning based algorithms required very high computation costs, and they're still facing some problems. They are not applicable for all means all type of hazy images. For example, like dense hazy images, or for night hazy images, still they are facing problems in a sharp region as well as in flat region also. Most of the times, deep learning based methods are facing some sky region problems. Sometimes they are very good to remove the haze, but still they are facing the problems in sky regions. And so next is the age preserving filters. Actually, in age preserving filters, we have to use some filter techniques right now. So in filter techniques, actually this filter is mainly designed to preserve the age information in the flat region as well as in the sharp region. Different filters are designed, and we have to classify these filters in a two is like that a local filter based and as well as global filter based. So local filter based means we have used a local linear based concept to preserve the age informations, and global age preserving filters are used global uh, means it uses a non-local linear model. Actually, the global age preserving filters use a non-local linear filters. So reason is that global age preserving filters have a more computation complexity compared to the local linear age preserving filters, and they are having very high cost compared to the local linear filters. So today we'll discuss about some local linear filters, because local linear filters are very good and they preserve the age information very effectively. And as our requirements, we can use local linear filters for removing the haze in the both actually flat region as well as in sharp region. So it is the taxonomy of image dehazing methods. I have shown the classification of the existing methods, how we can use this method: image enhancement based method, image restoration based method, fusion, deep learning, and age preserving filters. Right now. So, yeah. So first, I would like to discuss one age preserving filters. It is a local linear based filters, and how we use these age preserving filters to remove the haze, and how it is applicable for all types of age informations preserving for hazy image as well as for other types of images right now. So basic concept is that to preserve the age informations to remove the haze, uh, first I would like to show you, this is the basic flowchart of this. work actually. This work is done, and this work is presented in one of the journals, Circuit System Signal Processing, right now. So it is an edge smoothing weighing guided image filter, right? So this is a flowchart of the proposed algorithm. The complete proposed algorithm is divided into, as you've seen that complete algorithm is divided into 4 parts right now. So first what we do, here one input hazy image, we have a one input hazy image, and first we apply a dark channel prior, and DCP, it is the short name is DCP first, and after applying this DCP, we have a segment this input hazy image into atmospheric map and as well as into transmission map right now. And then after getting this transmission map, we have apply here one age preserving filters. It is a local linear based filter, single scale age aware filters, and its name is effective scale aware age smoothing, weighing constant based weighted guided image filter. And after applying this filter, we refine the transmission map and got the good transmission map. This is the basic initial transmission map, and after applying this filter, we got a very good quality of refined transmission map. And then we add our atmospheric map with the refined transmission map, and finally we got the DHS output image. So first I would like to discuss about the why we here I have applied a dark channel pair. Actually, DCP is a dark channel pair. It is based on the dark pixel concept, and how it works actually. DCP is based on the dark pixel concept. In the dark pixel concept, in any input hazy image, some pixels have a very low pixels value. Some pixels have a very low value actually. So these pixels value actually we use to calculate the atmospheric map. This pixels value is directly define the atmospheric map. If I find the atmospheric map, then we will calculate the transmission map from the our input hazy image equation, because in this equation we have one input hazy image, and second one is a haze free image, and third is a input transmission map or initial transmission map, and fourth one is a atmospheric map. So first, if I got the initial atmospheric map, then we can calculate our transmission map. If I know our initial transmission map, initial atmospheric map, then we are able to calculate the final haze free image right now. So from this image, we have to see here, we can see clearly input hazy image. So after applying the input, after applying the DCP, if your DCP is your dark pixel concept, it based on the concept of dark pixel concept right now, and we have to calculate the minimum RGB value from our input hazy image and find our dark channel prior. And next, after getting our DCP, we have to calculate our transmission map. It is an initial transmission map right now. So it is an initial transmission map, and finally we got our DHS image. How it works actually, we would like to show you the mathematical calculation here. As you know, the input hazy image from the starting of the slides, and first we have one input hazy image equation. So first what we do, we have to normalize this input hazy image equation by the atmospheric map. After getting the input atmospheric map, first we have to normalize and we calculate our initial transmission map. By dark channel prior, we have to calculate our actually it is based on your minimum RGB concept. So minimum RGB based concept means if you calculate your dark pixel concept, means if you calculate your dark pixel value, then you have to calculate your final atmospheric map right now. So and after solving this equation, we have to calculate our initial transmission map. After simplification, we have to calculate our initial transmission map, and it can be represented by this equation, equation number 5. Here, W is used for a constant parameter, where we have to set this value between 0 to 1. Actually, it is used to retain a very limited amount of phase, because if we set its value 1 means it defined as there is no haze present in your initial transmission map. If I put 0 means what happens? 0 means this image is completely fully hazy image. Means fully hazy means it is not nothings are visible inside this input image. So we have a the value omega here between 0 to 1. So after getting initial transmission map and atmospheric map, we apply a filter. It is a effective scale aware edge smoothing weighing constant with weighted guided image filter. So why we are applying this guided image filter? Actually, filters are available to remove the haze and as well as refine the transmission map, but still they are facing problem in the sharp region. So why we are designing this filter? Actually, reason is that because it is a single scale edge aware based. Single scale means here I have designed a one edge aware weighing. This is a edge aware weighing. Actually, it is an edge aware weighing. It is a local variance based. It is having a 3 by 3. 3 by 3 means if we set the window size 3 by 3, and if we set the window size 2 zeta 1 plus 1, 2 zeta 1 plus 1, so we can calculate our is aware weighing. Actually it is a single scale aware is aware weighing based uh, filter, and we can calculate by using this filter actually. And in window we have to calculate cost function. Actually, cost function, before going to calculate the final in solution of this filter output, we have to calculate some cost function. Actually, after solving this cost function, we have to calculate our linear coefficients right now. So linear coefficients is, if I got finally, then we have to simplify, or we have to calculate our final history image. So cost function is nothing in the guided image filter, as you seen that the cost function is used to measure the similarity between corresponding pixel value in the input image and the guidance image within the local neighborhood. As we know that the input image and guidance image may be the same or different, but here I have used the same input image as well, same input image for same input image and guided image right now. Because if we use a different input image and different guided image, means the complexity may be increased, and it increases the more complexity. So here I have used the input image and guidance image, both are same right now. So after solution of this cost function, we obtain the terms of two optimized linear coefficients. Here, as we can see that these two linear coefficients, A of k and B of k, we can calculate these two linear coefficients from after solving this cost function equation right now. So we have to simplify these equations and calculate these coefficients, linear coefficients like that. And after calculating these linear coefficients, okay, these linear coefficients, we are able to write the filter output in this form. Q of I is equal to AI bar I of I plus BI. AI bar and BI bar is your mean coefficients, and I of I is your input hazy image, and Q of I is nothing, it is your filter output. So filter output is what? Actually, filter output is nothing, it is your refined transmission map. Okay. After applying this filter, we got a refined transmission map. So refined transmission map means we have refined the age informations. We have refined the age information in the flat region, as well as we have refined the age information in the sharp region. So we have finally we have calculated this filter output here. Finally, the refined transmission map can be expressed by this equation right now. This filter output is the your final refined transmission map, and output history image we calculate by the scene radiance. Actually, this is the your final history image, and we have to calculate by this equation right now. So here actually T naught is fixed to 0.1 for our naturals, because if I use its value 0 or its value 1 means then 1 means what? It is actually a more means this output hazy image is having no haze information. Means it is clear. It is like a simple normal reference image, as you can see that. And T of if I put T naught is equal to 0 means it is completely blur image, so we cannot read anything from the input hazy image right now. So it is a finally haze-free image. So we have some experimental setup to justify our outputs, to calculate our outputs. So for this, actually, we have used 3200 images of indoor hazy image, outdoor hazy image, synthetic and dense hazy images for this work only. So and apply some data sets. Actually, we can see that here I have your fatal data set and NYU2 dense hazy data set, haze RD, and output hazy data sets. Different on different data sets. I have applied our methods on these different data sets and just calculate the output and verify if it is works on the flat region, if it work on this means sharp region. So I will show you. For example, it is an input hazy image, and first after input hazy image, after applying the DCP method, DCP is a dark channel as I have discussed before, and by applying DCP, we have to calculate the initial transmission map. It is an initial transmission map. You can see clearly this region is not actually clearly visible. This is the sharp region actually, and it is the initial transmission map. When I apply the DCP method, then we are able to calculate the initial transmission map and initial atmospheric map. Here in my methods, I have fixed initial atmospheric map value, and after setting initial atmospheric map value, we are able to calculate the initial transmission map. Okay. This figure is it is the output of input hazy image before applying the filter right now. So you can see clearly the edges are not clearly visible, right? So in the next figure, you just see here, after applying the filter, after applying the effective age aware, effective age aware filters means the proposed filter, we see the clearly, we have to clear visible, we have to see clearly the sharp region right now. So we are able to see the sharp regions information. So this filter is very good to preserve age informations in the sharp region, as well as this filter is very good to preserve age information in the flat region. So as you can see that, and the output of corresponding this input hazy image, as you can see that output is also the informations which are in the sharp regions, the informations which are in the flat regions are very good in the output hazy image. Means the filter, the proposed filter remove the haze very effectively in flat region as well as in the sharp region. So I have compared this algorithm with the another algorithms, means with the another existing algorithms, how this method is more effective. So here I have some comparison. As you can see, if I compare this method means initial transmission map with the another another filter refinement output of another filter. So as you see that the informations are not clearly visible in the this guided image filter as well as in the WGIF filter, means weighted guided image filter. Still they are having some problems in the sharp region, they have some problems in the flat region, they have some uh, over enhancement in the sharp region, as you see that, as you can see that. And next, it is the proposed method. If I compare our this method with the previous one, so in my methods, so edges are preserved very well, and this method is very effective, and it removes the haze informations. It removes the haze more accurately from the flat region as well as in the sharp region, and it is the corresponding output haze-free image of the other existing methods. You can just check this output of the other, and it is the proposed method. Here we can see clearly the output history image remove the haze more accurately from the sharp region as well as from the flat region right now. So it is another figures I have shown here to show you to because how it is more effective if I have a hazy image, more hazy image. It is a dense hazy image right now. So how this method is applicable for dense hazy image or not? So here first we are applying DCP method, and it is the output of actually DCP method. DCP method, as I know, DCP is a very basic method. It removes the haze information from the flat region as well as in the sharp region. But still, this method is facing the problems over smoothing as well as color distortion problems. As well as this method is not applicable for sky region problems, because in the sky region, as I know, in the sky regions, the colors we cannot clearly define the color of the sky region. Sometimes it is a dark black, sometimes it is a blue. So we cannot clearly define the sky region. So this method is not applicable for the sky region. Okay. So if I compare this method with the proposed method, so in this method, you can see the informations are preserved very accurately, and the information in the sharp region is also preserved more effectively. One thing I would like to show you here in the sharp region, as you see, some over smoothing are persist here right now. So when we apply some methods to remove the haze, they remove the haze from the flat region, they remove the haze from the sharp region, but still some over smoothing are present. So how we how we strongly remove this over smoothness, how we control this over smoothness. So we have to apply some filter algorithms. So like in my method, you can see there is no over smoothness. Over smoothness are present in the sharp region. So after applying the filter, we can control the over smoothness from the flat region as well as the over smoothness from the sharp region as well as from the flat region right now. So here is the different figures, as you can see. Okay. Here I have used one objective evaluation matrix. Actually, objective evaluation matrix is it is actually mainly because we have a one epsilon value. Epsilon value is used to calculate the haze informations in the how the filters are more effective in the sharp region. If I change this epsilon value is your regularization parameter, because we have designed I have designed one regularization parameter. So how the regulation parameter, if I change this parameter value, because in regulation parameter I have one variable parameter. If I change this parameter, so how its effects on the haze-free image in the output side. So if I change this value little bit of different, so we can see clearly the other filters have no good quality of haze-free image in the output side, but in this single scale Israel film filter, it removed the haze information, it removed the haze actually haze effect from the flat region as well as sharp region more effectively. This is the actually score which I use to calculate the haze information in the region. Next, we have used some performance comparison. For performance comparison, we have used some data sets, and these data sets actually used to calculate uh, some performance used to calculate some performance metrics for different methods, and we have to calculate and we have compared from the other existing methods. As you know, the PSN or SSIM is a very important these performance parameters, and by which we can just verify our algorithms with the other existing methods, how it is applicable, how it remove the noise from the whole flat region or whole sharp regions. So we can just calculate it. Here one another parameter is fade. Actually, fade is nothing. It is a fog aware density evaluation, and fade is if I have a fog aware density evaluation more in our haze-free image, in output haze-free image, means it is what? If you have a more fog in the output haze-free image, means it have a your filter, your method is not more applicable right now. If you have lesser fog aware density value in your haze-free image, then it means your haze-free image is more uh, dehaze, means it is more accurate as compared to the other output right now. So its lowest value is showing the good quality of haze-free image. And the another parameter is CID 2000, means it is a color difference parameter actually. If I want to calculate the color difference parameter from the input hazy image as well as from the reference image, then we apply this color difference parameter and we will calculate this this parameter and just compare with the other existing method. The same, we have used different data sets and applying on the different we have used here different data sets and applying on the different existing methods and compare with the other existing methods. So you just see here the proposed method having a good quality of scores compared to the other existing methods right now. So another table is very important table is execution time. How your method is more good compared to the other existing methods. If I change the pixels value, if I change the our means what we say that if I this method is more applicable for means execution, means more execution times it have, or it's have a lower execution times, or we can say that it is a having a good running time or not good running time compared to the other existing methods. So we have to calculate for different resolutions of our methods and just compare with the other existing methods. You have to see here I have used different like 250 by 200, 550 by 400, 850 by 600, 1000 by 950, 1200 by 1400, and finally we have calculated average value. So for different resolutions of images we have calculated the execution time, and from this execution time we are able to calculate the complexity of the methods also, how this method is more complex or not, this method is more having more running times or not. So as you see here, the proposed method having a good running time because it is a non-local linear types is preserving filters. If I use here a global type, means the global filters having a non-local, means it have a non-local type of filters and it have a more complexity compared to the existing methods. Its cost is very high and it takes a more execution time compared to the other existing methods. So another thing is that we have used some plots. Actually, it is a statistical illustration of your haze removal methods. How we visually so our method is good or not. So we here I have used a box plot. Actually, box plot is used to calculate your method is visually how we can say that this method is more effective or not compared to the other existing methods right now. So we have a box plot. We have calculated for the other existing method and compared with the proposed method. So how we know actually, as you see here, one median value is there. In each boxes there is one median box. So by using box plot, we have to calculate this median value. If the median value is lower, means if in the case of DCP, the median value is near about 20. In case of GIF, it is more than this 20 right now. So in case of this proposed method right now, the median value is more compared to the other existing method. Means if the median value is more, means your PSNR value is more. Means this method is having more PSNR compared to the other existing methods, and this method is more effective to remove the haze from the flat region as well as remove the haze from the sharp region right now. So we can apply these box plot for the other performance metrics. Here I have used the performance parameter for SSIM, okay, and calculate the box plot for the other existing methods and compare with the proposed method. As you see here, the median value is what? It is a near about 0.78 or 79, and other existing methods having median value more than this DCP value right now. But in comparison of the proposed method, all are having very less median value. The proposed method have a higher median value. Higher median value means it have a good SS charging value right now. So we can clearly see that yes, the proposed method is more better compared to the other existing methods. And this is the box plot, and we can directly show the outputs. We can clearly got the outputs. Okay, this method is more good compared to the other existing methods right now. So in the summary of this method, actually the main aim of this method is used to actually how to calculate the edges in the sharp region and how we can control the over smoothing problems in the sharp region. Number of methods are available to remove the edge from the flat region as well as sharp region, but still they are facing halos. Still they are facing some color distortions, and most of the algorithms are not applicable for the sky region problem. So how we can control all these drawbacks and how we can remove all these problems. So here we have used a filter, and in this filter we have a single scale Elizabeth filters, and applying this filter and remove the haze effect from the flat region as well as in the sharp region right now. So, but in the single scale Elizabeth weighing, still we are facing some one biggest problem is that one of the main problem over smoothing when I use this algorithm single scale is our being. So we are facing the problem is that when this method is applying for a dark hazy image, actually dark hazy image, so this method is still facing problem over smoothing. Means the previous method is not applicable for dark means dense hazy image right now. So how we can design another method, how we can implement one method or another methods to preserve the age informations for flat region as well as sharp region in case of dense hazy image. So we have a little bit of change in the previous method. Here I have used a multi-skill Elizabeth weighing. So what is the changes in the multi-skill? Everything is all same. Here I have changed one filter, and Elizabeth weighing are also changed here. And by changing this algorithm, by changing this small part of the filter, we are able to calculate the age information in the flat region as well as we are able to calculate the age information in the sharp region, and we are able to control our over smoothing problem in case of dense hazy images. So this paper is published actually in Journal of Signal Processing System. It is a multi-scale laser weighing based gradient guided image filter. So the proposed method is divided into 4 parts. This is the basic block diagram of the proposed method. Okay. So here, as a previous, we have a one input hazy image right now. First, what we do, we have applied a DCP method. DCP method is nothing. It is a dark channel pixel based concept. It preserves the age informations. Actually, it segment your input hazy image into atmospheric map and in transmission map right now. So after getting initial transmission map and atmospheric map, we are apply the filter actually. This filter is a multi-scale laser weighing based gradient guided image filter. The concept of this filter is it is a gradient guided image filter. So gradient guided based filters use some gradient concept actually. It uses some gradient concept to preserve the age informations from the sharp region as well as from the flat region very effectively compared to the previous single scale laser weighing filter right now. So after getting the initial transmission map, we apply this robust scale aware based effective age preserving gradient domain guided image filter, and after applying this filter, it segment the initial transmission map into 2 parts actually. One part is effective weighted base layer. Base layer is your main input initial transmission map, refined transmission map, and another part is your noise part, or what we call it is a effective weighted detail layer. Means if it is in detail layer, is are not available, so we are able to say okay, in this region, in this sharp regions, the edges are not preserved clearly. Okay, so if the edges are not preserved clearly in this sharp region or in flat region, so after that we have applied one non-linear mapping concept. Actually, non-linear mapping concept is some contrast enhancement based concept to preserve the edges in the sharp region right now. And after getting this region, and we add all these terms: atmospheric map, effective base layer, and our non-linear transmission map output. And finally, we got the his output, history image right now. So I will discuss one by one. As of I discussed, it is a robust scale-aware weighing based filter. So in this filter, this term is actually your new scale-aware based age-effective gradient domain varied image filter. It is an age-aware weighing filter. This age-aware weighing filter is different from the previous one because it is a gradient-based filter, gradient-based age-aware weighing concept. So in this, we have defined this term actually by using some variance of 3 by 3 window, by using some variance of this 2 zeta 1 plus 1 by 2 zeta 1 plus 1. It is a window size. Okay. And after designing of this is we are weighing, we have calculate our cost function actually. Cost function, as we discussed, the cost function is used to measure the similarity between corresponding pixels value in the input image and the guidance image within the local neighborhood right now. So we can calculate the cost function from here, where gamma k is actually it is used to uh, find the age information. If I put the gamma k is equal to 1, means what? Pixel k is it in sharp region, or if I put a gamma equal to k is equal to 0, means if it is pixel k is at a flat region. Means if gamma k value is 1, means k should be on sharp region. Means if your k is at, if you know the k is at a sharp region, then gamma k should be 1. If it k is in flat region, then gamma k should be 0. Right now. So by using this condition, we can also check our method is good in sharp region or our method is not good in sharp region. If this condition is follow this, if this algorithm is follow this condition, means we are able to calculate the age information in the sharp region. We are able to calculate the age information in the flat region right now. So after applying this cost function, after simplifying this cost function, we calculate these linear coefficients. These linear coefficients are very important to finally calculate the your filter output. So after simplification, we have to calculate about these linear coefficients. Okay. So after getting this filter output, right now, final output of this filter output, we are able to calculate our refined transmission map. So here we have to calculate our refined transmission map from this equation. And next is, as I have discussed from the flowchart block diagram, after applying the filter, we have segment the input initial transmission map into two parts. First is effective age aware base layer, and second one is effective age aware detail layer. Detail layer means it is nothing, it is your noise part actually. So it may be possible some part of informations are maybe in your detail layer. So how we can preserve this main information from the detail layer right now? So if I use some algorithms to preserve the age information from the detail layer, so here I have used one non-linear Laplacian mapping function to preserve the age information from our detail layer. It is a well-defined method. Actually, it is based on gradient enhancement gradient informations. It is used to calculate the information from the detail layer right now. And finally, after applying this non-linear mapping function, we have to calculate our final H-free image from the scene radiance. As I have discussed in the previous, we have to calculate our H-free image from this equation, where this input Ix is nothing, it is your input hazy image, and A of C means it is atmospheric map. For C stand for color image right now. So, and here I have used more data set compared to the previous one. We have more data set to check the history, check the output of our methods, how it is more effective compared to the other existing methods, and how it is effective for the dense hazy image, how it is effective for the uh, homogeneous hazy effect, how it is not effective for non-homogeneous. So we can have different types of data set here, and we apply these data sets on our methods and compare with the other existing methods right now. And here also we have some performance metric. By using this performance metric, we have to calculate, okay, yes, this method is more applicable, more advantage compared to the other existing methods or not. So just for comparison, as if you have seen that which is the input hazy image, and it is the output of DCP. Okay, DCP, as I have discussed before, DCP is a very simple and very effective methods to calculate the atmospheric map and transmission map, but still it have a more problem in a sky region. As you have seen here, some part of the sky region is very looking very sunny type. So it is some color distortions are available here right now. So that's why this method is not applicable more in case of sky region or in sharp region, or some still they have some color distortions also. And these the guided image filter. In guided image filter, as I have discussed, guided image filter preserve the information very good in flat region, but it's facing more problem in the sharp region. As of you have seen that the regions are not clearly visible. Okay, so still they are facing the more problems. Here I have applying more methods, more filters here, different local linear based filter, and as you have seen that the output of the proposed method means the edges are more clearly visible in case of this proposed method, and we have able to see the edge informations in the flat region, edge information in the sharp regions, and there is no over smoothing, no color distortions are available right now. As of you have to see here some distortions in color, some distortions in colors are available right now. So here is another methods I have used to show you how it is applicable for the different images, different. So visual qualities, from visual quality we can say that okay, this method is not more applicable compared to the other existing methods. They have some problems in the flat region, they have some problems in the sharp regions, still they are facing some color distortion problem, halos region. Okay, so for performance comparison we have different data sets. Okay, and here I have used some reference and non-reference bits performance metric. As you know, some reference performance metric means the reference performance matrix means which the performance or which the data sets have a input ground image, like ground truth image. So they are the reference image. For non-reference based means there is no need to ground truth images. Okay, so we have applied different. We have applied the on different data sets, different methods, and calculate the performance parameter. Here I have used some different performance parameter VCM. Actually, these three are E, R bar, alpha bar. These are the contrast metrics. If you want to calculate the contrast metrics, means when we are applying our methods on any input hazy image, so you have, okay, there is no problems. You got the in the output hazy image, but what is the problem? There are some contrast enhancement. Means some enhancement problem is there. Means some part of the in your output history image, some part of the image are very enhanced, they have more contrast compared to the natural enhancement, like, okay, so how we can calculate? So these are the performance metrics by which we can calculate and we can compare with the other existing methods. And this is a contrast gain. It is also one contrast metric. VCM your visual contrast metrics right now, and these SSI and PSI I have discussed before as well. EKI is your new performance metrics. It is a age keeping index. Yeah, it is a very important performance metric actually. Age keeping index is used to calculate particularly how we can know key ages are preserved in the flat region very clearly, ages are preserved in the sharp region very clearly, and still they are not facing the over smoothing effect. So here these EKI means age keeping index is used to calculate age informations in the sharp prism as well as age information in the flat prism. So as you see here, the informations means the score of the EKI of the proposed method is what higher compared to the other existing methods. Means this method is more applicable. This method preserve age informations in the sharp region. This method preserve the age information in all the regions more accurately compared to the other existing methods right now. So that's why this method is more applicable. Why this method is applicable? Because this method is particularly designed to calculate the age informations in the sharp region, flat region, and they control the over smoothing effect. They are able to able for dense hazy image also. So this performance parameter we have to use to calculate all the okay. So the another is I have discussed it is a color difference matrix. Fade is used to calculate fog aware density evaluation. Right now, I have discussed if it is value is lower means you in the output side your haze free image is more clear compared to the means input haze image of other existing method. CNI is your color natural index, okay, and it is an universal image quality index. These are the performance metrics by which we can calculate and we can compare our methods. Okay, how this method is more advantageous, this method is more accurate compared to the other existing methods. So for this comparison, I have used different data set and calculate the performance value for different data sets and compare with the other existing methods. Okay, we have to see here. You can see there are some FRIDA data sets, some output hazy data sets right now, and it's a average execution time actually. So how this method is more having good execution time compared to the other existing method. We have a different resolutions of image, and we have applying on the input hazy image and compared to the other existing methods right now. And we can see that the proposed method have a very less execution time compared to the other existing methods. It is more good. It is more what we say that it is a less execution time compared to the other existing. If the resolution of time is increases means its execution time is also increases, but compared to the other existing methods, the proposed method have a lower execution time compared to the other existing methods. Means this method have a lower complexity compared to the other existing method. It is a very good in what we say that in complexity as well as in the running time. Okay, so here I have used a box plot. I have discussed the why we are used box plot. If I want to calculate, if I want to visually, so how we can calculate this method is more good or this method is not accurate compared to the other existing methods. So here I have used a box plot actually right now. So box plot, there is a median value, and by this median value we have idea actually. Yes, this method is more accurate compared to the other existing method for this particular performance metrics. As you see here, this method have a more median value compared to the other existing methods. So I have calculated for all the performance metrics this box plot and compare with the existing methods. So as you can see, the proposed method have a good uh, median value compared to the other existing method. Means this method is proposed method is more accurate compared to the uh, other existing method right now. So we have calculated this box plot for all the performance parameter and compare with the other existing method. And finally, it is a summary of this work actually. It is a robust scale aware based weighing based effective speed filter, and it is based on a multi-scale as filter. It is a gradient domain based guided image filter. It is a non-local linear type filter. Means it is a good for uh, it is a good in case of complexity also. right now. And it preserves the age informations very nicely in the flat region as well as in the sharp regions. It removes the halos, it removes the color distortions, it removes the over smoothing from strongly from the flat region as well as in the sharp region. And this method is independent of the nature of the input image and performs actually equally well for all data sheet. And next last what we say, it is it is a good for processing timings. It requires a very less execution time compared to the all compared to the other existing methods. Okay. So okay. So any questions? Hello.
Yes. Sir, completed, sir.
Yes, sir.
Okay.
If any
Thank you
questions.
so, thank you so much, sir. Any questions from audience? Any questions, sir? Participants?
Yes, sir. Sir, in this we have calculated both atmospheric map and transmission map. So
Yes.
from how did you calculate that atmospheric map? Because from dark channel prior we will get the atmospheric light. JTLC is space force. That's the code. So how you are able to calculate both the atmospheric map and what is the indication of the transmission map? What does it infer?
Actually, to calculate the atmospheric map and transmission map, actually we have no directly methods right now because haze image is having a ill-posed nature right now. It is there is no methods, there is no fixed methods are available to calculate the haze effect accurately right now. So there is a one method DCP. DCP is based on the dark channel prior concept. In DCP, we have used a dark pixel concept, means in some of the RGB channels, in any channels, they have a less pixels value. Okay, less pixels value means what? This less pixels value declared the atmospheric region. If I know the atmospheric region, means atmospheric region means your atmospheric light. Okay, if I know the atmospheric light, for example, if I told there is a one building, okay, so in the building of what we can say that in the shadow of car there is some informations. If you see some part of the your means what we say that is looking like a dark when you see some building parts from the window side, the window, what we say that it is a some part is not visible clearly, some shadows are available. So some shadows are available means what? Shadow means what? The pixels value is very less here. Okay, so if I know pixels value is less means what? We have to fix this pixels value. Okay, this dark pixels value. Dark pixels value means what? The pixels which have a very low intensity value. So if I know this pixels value, then we are able to calculate the another terms transmission map. So for these applications, for this requirement, I have used a DCP method. DCP is a very simple and very effective method. When I use this method on an input hazy image, it segment the input hazy image into two parts. One part is initial transmission map and another part is your initial atmospheric map. And if I know the initial atmospheric map, then we are able to calculate this initial transmission map. The main role of your haze-free image is your initial transmission map. If you got the initial transmission map, means you are able to calculate your final haze-free image. Right now.
Sir, the transmission map is defined by T of X now, sir.
Yes,
that
yes.
we will get from the dark channel prior.
Yes.
So the color change in the transmission map indicates where there is more fog like that, or what is that color change indicates? Or is the depth of the image like that?
Yeah, actually, this transmission map we cannot. We have to calculate. If you got the initial transmission map, yeah, you are able to calculate your haze-free image directly. There is no issue. But problem is that if you got your initial transmission map, but this I have shown some of the results in visual results where we have initial transmission map, but initial transmission map, some flat regions are visible, no issue, but some sharp regions are not visible. We have not calculated the sharp regions very accurately. So how we can calculate this sharp region? So to calculate this sharp region and to control the halos as well as to control the over smoothing effect, here I have used some filter because these filters are very effective. These filters are defined to calculate your age informations. These filters are refinement based. Refinement means if any informations are not preserved clearly in a particular your ages right now. So how we can calculate by applying this refinement filter? If I apply this filter means this filter preserve the age information in the particular your like a sharp region in your particular what we can say that some specific reason. So we are able to calculate this. Otherwise, it is very hard to calculate because number of methods are available. They are very good. They remove the age informations very effective, but still they are facing over smoothing problem. So how we can just control this over smoothing problems? How we can control the sky region problem? Because in as you see some hazy images, some sky region problems are available. Methods are available, but still they are not applicable for all the types of hazy images. Because in hazy images, some images are homogeneous based, some images are non-homogeneous based. So how we can control it? So to control it and to preserve the age information in the flat region as well as in the sharp region, filter is very important. Filter, if you use the filter means you are able to calculate your age informations in your flat region as well as in the sharp regions, and you are able to calculate your informations as well as you are able to control your over smoothing effect right now.
Yes, I have one more question. Why didn't you go for some contrast limited adaptive histogram equalization methods?
Which one?
Contrast limited adaptive histogram equalization methods, paint methods. Because it also it can enhance the image now.
Actually you are talking about non-linear mapping function.
Histogram equalization method.
Actually, your voice is not clearly. I'm not getting your point.
Thank you, sir.
Hello, Sumit sir.
Yes, sir.
Thank you so much, sir, for your expert lecture. And mm, any questions, or shall we stop here? Okay, sir. Sumit sir, we can stop. Sir.
Okay, sir. Thank you. Thank you very
Thank you.
much.
Thank you,
Thank you.
Sumit, sir.
Okay, sir. Thank you.
Valuable session. Yes, thank you.
Thank you, sir.
So, yeah, dear participants, the next session will resume at 1:15. Now lunch break. Thank you. Very good afternoon. Welcome back to day 3 of 5 days FDP cum workshop on contemporary image processing and cybersecurity application. The afternoon session resource person is Dr. Priyadarshini ma'am. She is working as an assistant professor in the Department of Computer Science and Engineering, IIIT Kottayam. She has received a Bachelor of Engineering and Master of Engineering in Computer Science and Engineering from Government College of Engineering, Tirunelveli, Tamil Nadu, and PhD from NIT Puducherry. Her research area of interest is spherical video summarization. During her doctoral research, she has published 7 papers in international peer-reviewed and reputed journals, including 1 book chapter, 1 conference proceeding. She has also published a patent related to her research work. Let us join with me to welcome Dr. Priyadarshini ma'am. Over to you, ma'am.
Thank you, sir. Thank you, sir. Good afternoon to one and all present here. So I'll share my presentation first.
Yes.
Sir, is my presentation visible,
Yes,
sir?
ma'am. Visible,
Oh,
visible.
okay. Okay, sir. Thank you so much, sir, for your warm welcome.
Thank you.
So now I may proceed with the content. So good afternoon to all the participants who are available online. So my sir, is my screen fully visible or it is
Yes, ma'am,
visible?
it's
No?
moving.
Oh,
Fine.
okay, sir. Okay. So in today's session, I will be discussing few things about spherical video summarization using optimization technique. So myself, Dr. Priyadarshini, Assistant Professor in the Department of Computer Science and Engineering from IIIT Kottayam. So the main content what I want to talk or specify in this session is how to do video summarization in spherical video. So what is the spherical video? How this video summarization is happening in spherical video? What are the 4 different approaches how we can do it with the help of an optimization technique? So this is the theme which we will be taking today for this session. So so the outline for my presentation for this session is I will be giving a short introduction of what is spherical video and the motivation behind going to this spherical video. What is the goal of this complete spherical video summarization process and the contributions of what I'm going to discuss in the next coming slides. A few survey about what are the available works that are there in terms of spherical and non-spherical video. And our session will be covering video summarization in terms of both temporal summarization as well as spatio and temporal summarization. So starting with the introduction to what is video summarization. So why should we go for video summarization? So it comes from the beginning of all the application that is involved with the video. For example, let us assume a surveillance camera. So the surveillance camera, the main purpose of the surveillance camera is to record the activities that is happening on the specified region 24/7. So now at the back end, sitting and viewing this entire video is a tedious task. So day by day, what is happening? The amount of video captured is growing dramatically. Either it can be in public or private places. So mostly when we talk about a public place, the number of people who are coming or who are using that space, that particular public space is overloaded compared to that of private places where the population is very less compared to the previous case. So in that way, what is the best solution to view the activities is the video summarization. So the public places can be airport, museums, or any kind of places where the population is overloaded compared with that of private places. So this is the exact initial process or initial reason why we are using surveillance camera. So the surveillance camera is mainly used to see the activities that is happening in a particular place. That may be either a private place or a public place. Now, when we come to see what is the problem in using the surveillance camera, as I have already told you, the surveillance camera keeps on recording the activities for 24/7. So now what happens when a person want to view a particular region or particular place in the surveillance camera at a particular fixed time? So what he has to do is he want to capture or he want to see all the activities, keep in record of all the activities that is being happening from the initial state to the end state time. So now where the problem is, why should he sit for one particular activity to see one particular activity from the start of the recorded video to the end of the recorded video? So that makes a little bit tedious work to sit and identify a particular moment which he is interested in. So this is one problem with surveillance camera videos. Now, how we can solve this? So video summarization will come us to help for that particular problem. So one way what he can do is fast forward the recorded video until he reaches the place or the time where he is interested. Or the second one can be selecting the key frames for a particular time period and then visualizing that key frame for the particular event which or the activity which he is interested. So that key frame selection can be either arbitrary or dynamic. Arbitrary in the sense simply selecting all the frames. So I believe that everyone is familiar with what is frames in a video. So a sequence of frames are put together to form a video. So video is nothing but a sequence of frame which is being recorded, or it is composed of a multiple number of frames together, which is processing in a given time. So the video summarization can be done by keyframe selection, that is arbitrary selection or dynamic selection. This dynamic is something which is according to the activity, the algorithm will select more frames from the activity. So if you see these two solutions all deal with the frames. So frames is nothing but building blocks of video. Now, how to extract the important frame is known as video summarization. So if I have to give a definition for video summarization, it is the selection of the important activities or important frames in the video to view or to get a complete picture of the important events that is happening in an entire or a full recorded video. So this is the introduction for video summarization. Now, how is it happening? If the users would like to watch a complete video which is recorded for last week in 5 minutes, this is the query that I am requesting to the model, or this is the need of the user who want to view 1 week recorded surveillance video in a 5 minutes. Means what can be the background application, or what can be the background process that can take places? The model will identify the important activities that has happened for last 5 minutes, and it will try to stuff it within 5 minutes. So at the goal will be, let us say I have 24/7 hours video for 1 week. So that much amount of lengthy video will be shortened into 5 minutes by identifying only the key activities. So when I say key activities, what can be the key activities? It can be something that the frames which include objects. There may be some situation where the surveillance camera is recording the scene which has no objects involved. There is no movement. So those kind of unimportant or those kind of unnecessary activities can be removed from during video summarization. So that is the goal of video summarization. So the next one is what if we have to say in terms of the technique that is used is we will name it as indexing. So this indexing is nothing but identifying the key important events or activities and giving them an index value, and based on their occurrence in the original video, we'll be trying to put them or stuff them in the output video. So the idea is to create a video synopsis according to the user query. My user query is to generate 5 minutes synopsis video of the long recorded surveillance video of last week. So the video will contain the important data and activities from the raw data, from the raw video, and then the video synopsis will contain the important activities, data and activities from the different times. So each activity will have a pointer. So this is what I mean as indexing. So each activity in the video will have a pointer in the original time and space in the raw video. Now that pointer along with the activity will be tried to stuff into a 5 minutes synopsis video. So throughout this session, I'll be talking about two videos, input video and synopsis video. So input video is a long recorded video. Synopsis video is the output video, which is obtained as per the user request query. So now the approaches to perform video synopsis is normally of two kinds. One is pixel-based approach. So I assume that everybody knows what is pixel. So if you talk about frames, image processing, video processing, pixel plays an important role. So when we do our video summarization in terms of pixel, which is a low-level based approach, is pixel-based approach, where we concentrate on the pixels of each frame in the video. It is known as low-level representation, whereas we have another approach, which is a high-level way of representing a video summarization, is known as object-based approach. So this is what we are going to focus more about. In this session, we are going to focus more about object-based approach. So when you compare a pixel-based approach with an object-based approach, the object-based approach gives us a better solution compared with that of a pixel-based approach. So a pixel-based approach is taking each and every pixels, and then we are trying to find the important activity of that particular pixel in that particular activity, which will provide us a very less level of approach or less level of representation. Whereas when we move towards the object-based approach, can provide us a more in-depth view of the activity which is being recorded in the surveillance video. So this high-level object-based approach will be something which we will discuss in this session. So now the past 2 to 3 slides was a short introduction for video summarization. If I have to recall, video summarization is something which stuffs the long recorded video into a shortened form, where we will be able to see only the important activities that are happening in the original video. Now moving into the introduction of spherical video. So what is spherical video? 360-degree videos are also known as spherical video. So what is the opposite, or what is the other videos which we are normally using is known as non-spherical video, which can also be termed as traditional videos. So non-spherical videos are videos which we use, or which we are more familiar with. The videos which we see, which we use in our laptops, which we see in our TV, which we see in our mobile. So these videos are non-spherical videos. So what is the difference between non-spherical and spherical video is just the field of view. So you can see here, in spherical video, the area of interest is something which the user can decide. So now one of the application which is most familiar for 360-degree video is known as Insta360 application. So here you can see, this is a frame from the recorded video. So here you can see my field of view. I can change my field of view wherever I want. So in case if I want to view this region, then I can see this region. I can zoom in and see this region. If I want to see some other area, if I want to focus on this vehicle, I can move my field of view. So this is one advantage compared to that of non-spherical video. So this is another frame. So in this frame also you can see, I can able to shift, or I can able to select my own field of view. where I want to focus my area of interest. So this is the only difference from non-spherical video to spherical video. So this spherical video records the scene in all direction, which is not possible with the non-spherical cameras or non-spherical videos. So it offers unlimited field of view. So as I have told you, I can see wherever I want, but this is not possible in non-spherical video. In non-spherical video, what is happening is I am fixed to my field of view. I cannot change my field of view. But the advantage that spherical video provides is unlimited field of view. So what is this field of view? I'm continuously telling the advantages field of view, field of view. So what is this field of view? Field of view is nothing but a small portion which is visible to the viewer. So in terms of non-spherical video, the FOV or the field of view is fixed. Whatever is seen there, if you see a movie, we are seeing the movie only from the director's perspective. Whatever the director is wishing to show in the screen, we are only able to see that. But if you are using a spherical video to record that particular scene, the viewer has the more chance to see in the movie whatever he is interested. So ultimately, the advantage of using spherical video is more compared with that of a non-spherical video. So that is known as field of view. Now, when I talk about this field of view, where I'm able to see whatever I want to see, the FOV is not fixed. So how is it possible? It is possible by using this pitch angle and roll angle. So 3 angles will come into picture in spherical cameras. So which is nothing but horizontal, vertical and roll angle. So the angle, which is horizontally, it extends from -180 degree to +180 degree, whereas the pitch angle extends vertically from -90 degree to +90 degree, and the roll angle is something which is to make view of the particular scene in a very proper way. That is, to understand the scene in a better way. By default, every spherical camera uses the roll angle set to be 0 degree, whereas this angle ranges from this range, pitch angle ranges from this range. So whenever I want to see a particular view, what I do, I am just trying to change my angle and my pitch angle, whereas my roll angle will be fixed. So when I change my angle and when I change my pitch angle, I will be able to see the particular area of interest which lies in that and pitch angles. So this is an introduction for what is spherical video. So now moving on to the next one. What is the observation? So far I have discussed what is video summarization, what is the difference of non-spherical video with the spherical video, what is the advantage of using spherical video. Now, if I move into see what is the observation. So first of all, I want to make one thing very clear. Why in surveillance we go for non-spherical video is because of this whole field of view. Let us assume there is a road in a city which is to be monitored by using a non-spherical camera as well as a spherical camera. So when you use a non-spherical camera, the field of view is fixed. So at the viewer end, the viewer is forced to see only that particular direction of the road. But same thing, if you replace with the spherical camera, you will be able to see all the direction of the road, that is 360-degree view of that particular road, where the viewer can or the user can change his field of view to see whichever road or whichever path near to the road he wants to view from at the back end in the surveillance video. So now we will see what is the observation in terms of video summarization. So initially, there is no research work which has taken the spherical surveillance video for the object-based video synopsis. So video synopsis is not a new term. I have already told you in this full session, I'll be using 2 terms, input video, synopsis video. Synopsis video is nothing but the output video, which I'm going to create a stuffed representation of activities. And the second observation is the surveillance video synopsis is generated And there is no, even if there is some works on non-spherical video also, the action recognition part is not done much with the spherical video. So this is the second observation. And the third observation is, when we see the literature survey, you will understand this point number 3. But I'll just tell you the point number 3. What the point number 3 observation states is, there are works which work on multiple number of field of views, which is having at least 12 normal field of view. So the observation number 3, you will come to understand more in detail when I discuss in literature survey. But here what I want to stress is that there are various video summarization for spherical video, but not an object-based approach. That was my first observation. My second observation is, there is no work which is related to action recognition. And my third observation is, there is no any work which does video summarization with less than 12 normal field of view. This is the third observation. And the fourth most challenging observation which we observed is that when we play a frame, what is frame or what is field of view, which is something which we are able to see. For example, if you are watching a scene, or if you are, let us assume you are watching a movie, to the maximum number, the particular scene or particular frame in the movie can contain the characters which are needed for that particular scene. You cannot stuff it with other characters which are not needed in that particular moment of time. So what is the observation we obtained is, by providing or by stuffing more number of objects in one single frame, will try to deviate the viewer's importance or the viewer's attention towards that particular frame. So our fourth observation is to make a constraint of number of objects that is displayed on the frames. And the last or the very important one is fear of missing out. As we have seen, the spherical video has an advantage of providing the viewers flexibility to see wherever he wants. But what is the problem in that is, when he is viewing one frame in the complete 360-degree view, he is forced to miss the other views which is happening in the behind him. That is, in the 360-degree view, if he is focused on one area, he is forced to miss the other areas or the other regions which is not under his focus. So this is known as fear of miss. How to tackle these problems? This is what the theme or observation which is observed. Now in the next coming slides, I'll be discussing the solutions for these, so that we will be trying to solve these problems. So the solution, solution for this observation is, we are trying to make use of only 4 field of views. As I have already told, there are works which focused on at least 12 FOV. So in what we have observed is, if there is a possibility that this 12 can also be decreased to 4 by having a less number. Instead of 12, we can use 4, so that the number of field of view that is being used is reduced. We are providing the user a flexibility to limit the number of objects displayed per frame. So if I have to explain the second solution, it is something with that of the video which you are watching. Let us take a video. In that particular video, if there is a main character in the video which is playing a role, what we can do to the maximum is supporting to the main character what are the objects needed. Only that will be visible in that particular frame. We need not include all the objects in the frame which is going to appear in the video, particular in the entire video. Okay, so second point, now you may not be clear what I am talking, but when I talk more in detail, you will get what it is actually. And the third solution is to generate an action recognition based spherical video. So in the surveillance video, there can be any activity that can happen. For example, if I keep a spherical video on the same example on the road, which is, let us say, my spherical video is recording the entrance of a college, or it is placed somewhere in the busy city, in the road of a busy city. So what happens? Any kind of activity in the road is in that public area is possible. It can be either running, it can be walking, it can be jogging, or it can be anything. So what we do, we can concentrate more on action based video summarization also. That is the third solution. And the fourth solution is, instead of making a viewer to view, that is fear of missing out, instead of making the viewer to have fear of missing out the other areas, we can make a dynamically generating video synopsis based on the viewer where he is watching in the surveillance video. So as I have discussed the observations and the solution for that, now I'm trying to classify this solution into two kinds. So one is temporal summarization and one is spatio-temporal summarization. So what is temporal summarization is, it is something which is time-based. So I'm trying to reduce my long recorded surveillance video into a shortened video. For example, like how we have seen in the initial user query. I want last week surveillance video into a 5-minute synopsis video. So 24/7 recorded each day last week, 7 days, 24/7 video is converted into a 5-minute synopsis video. This is known as temporal summarization. Then what is spatio-temporal summarization? When I try to reduce the size of the video, length of the video, as well as the space of the in space domain. What do you mean by space domain? My 360-degree view is going to be summarized in a shorter way so that I'm trying to cover only the interested field of view. So if you see here, I have 360-degree view. From this 360-degree view, I will be trying to select the field of view, wherever there is an important activity that is happening in each FOV, and I will be trying to do it, creating a shorter video for that particular field of view. So this is known as spatio-temporal summarization. I'll repeat again. So temporal summarization is something where I'm trying to do summarization along the time axis. Spatio-temporal summarization is a summarization approach where I'm able to do in both space as well as time. So these are the two categorization of how the video summarization can be done in spherical videos. So now if we see the contributions, or what is the thing we are going to talk in the research of doing video summarization for spherical video is, we will try to restrict the number of objects to be displayed per frame. We propose, or we try to introduce an object-based approach for video synopsis, and then we see how to visualize them. So now, if we have created a spherical synopsis video, which is nothing but an output video, now the challenge is how to visualize them. There are two approaches to visualize them. One is direction-based approach and another is a customized approach. What is it? We will talk about it in detail. And the next stage is personalized video synopsis. So why should I generate a video synopsis for every field of view? Instead of generating field of view for every 360-degree video, what I can do, I can select only the interested field of view, and from that interested field of view, I will be trying to generate a video summarization. So how can this be achieved? In an effective way, we came across and we proposed an algorithm, optimization algorithm, which helped us to generate in a very effective way. So once right now what we came through is what is video summarization, what is spherical video, and what are the challenges or the observation we have seen from the spherical video summarization. Now in next 2-3 slides, we will see just the survey of existing works in terms of spherical video and non-spherical video summarization. So survey on spherical video summarization states that there are works in both spatial and spatiotemporal summarization, but you can see the last column where you can see 18 azimuthal and 11 polar angles are used. Altogether, the product of this is 198 glimpses. What do I mean by glimpses? The field of view. So from this spherical video, 198 field of views are extracted. Important key activities of 198 glimpses are obtained from this. So the initial work of spherical video summarization was started with this process only. So in 2016, Su et al., they proposed an AutoCAM model which makes use of logistic regression to create a video summarization of 198 glimpses. Now, the same authors, they extended their work with the help of zooming. So when we do video summarization, if we are more interested in particular activity, we can zoom in. So this particular authors, what they did, they also proposed with the zooming concept with the same glimpses. So 18 azimuthal is nothing but horizontal angle, which is yaw angle, and 11 polar is nothing but the pitch angle. So they used a combination of 18 horizontal angle and 11 vertical angle to come up with the video summarization. In the same year, Hu et al., they proposed a video summarization with no glimpses. So what do I mean by no glimpses is they don't have a fixed field of view. Just they used the input spherical video, and then what they did, they just created randomly. They created a video summarization for the glimpses which had glimpses. What do I mean by glimpses is nothing but the field of view of all the things whichever is available. So now the next one is Yu et al. So now Yu et al., what they did is they are the one who used both spatial and temporal approach. They used a composite view score. So what is this composite view score is? For the entire 360-degree video, for every field of view, a score will be given. For this view, a score will be given. For this view, one score will be given. So how the score is given? Based on the activities that is involved in that particular view. So the another advantage of this work is they reduced this 198 glimpses into 12 glimpses. So you can see that the usage of field of view is reduced to 4 horizontal angle and 3 polar angle. And in the next same year, Lee et al., they used past future memory network to provide a video summarization with 81 glimpses. So 81 field of view was used, which takes 9 azimuthal angle and 9 polar angle. So these are the few works which was focused towards the spherical video summarization in terms of both spatial and spatiotemporal summarization. And the main thing to be focused is the glimpses. How many field of view have they used to create such video summarization? Now, moving on to the next, we are seeing the survey on non-spherical video summarization. So what is, how are the works available in the non-spherical video summarization is, initially it started with Pritch et al. In 2008, where they used an application of generating non-chronological synopsis video, where the activities are stuffed into an output video. The parameters, the optimizing parameters are activity, collision, and temporal cost. So what is these cost? I'll let you know when we discuss more in detail. Through this survey, I just want to showcase that what has happened in their work. So what is this activity cost, what is collision cost, and temporal cost? We'll discuss about that in detail after once this survey gets over. But their work is not focused on action recognition, and the length is not optimized. So what do I mean by length optimization? What is my major goal in doing video summarization is, for example, it is just like a instead of watching a 3 hours or 2.5 hours movie, you are trying to see only the key events in the movie. Let us say the 3 hours movie is shortened and given to you for just 30 minutes. So then what does it mean? What are the key events in the movie has been reduced or condensed into a shorter video of 30 minutes. So this is known as optimizing the length. So that is not done in the initial work, which was started in the first started. Then in 2016, so there is a gap between 2008 and 2016. It doesn't mean there is no work that exists in this area in this year. I'm just trying to focus the key events. That's why there is a gap. In 2016, Mahapatra et al., what they did, they came up with an approach to do both action recognition as well as optimizing the length of the output video. And in the next year, 2019, after 2016, in 2019, it was Ahmed et al. Who provided an spatiotemporal grouping to perform the optimization. But the problem is they did not focus on action prioritization and optimizing the length. Then in 2020, Ghatak et al., they proposed an optimization algorithm, which is an hybridized simulated annealing with teachers learning-based optimization algorithm. And in the same year, they also proposed hybridized simulated annealing with the Jaya algorithm. So these both was done by the same author, but with a proposed optimization algorithm. And next, in 2020, Namita and Narayanan, they proposed an length optimization. So their focus was only on the length. They didn't focus on activity, collision, and temporal. They only focused on length. And in 2021, the Ghatak et al., they proposed another optimization algorithm in addition to this simulated annealing with TLBO, simulated annealing with Jaya, as well as simulated hybridized gray wolf optimization with simulated annealing. So that's all about the survey on non-spherical video synopsis. So what we saw in the survey is, literature survey is, we had two parts, spherical video summarization as well as non-spherical video summarization. In spherical video summarization, we saw that people were using at least 12 NFOV, that is at least 12 field of view to create and summarized one of the input video. Whereas in the non-spherical video, we saw many people who developed their own algorithm and a model to perform a video summarization. So with this information, we will dive into the spherical video summarization in 4 different ways under the classification of temporal summarization and spatial summarization. So the first one is the spherical video synopsis generation framework with direction-based visualization. So once I generate a spherical video synopsis, how should I view it? So that is a challenging part. So only generating is not a process or not a challenge with the spherical video. Visualization plays a major role in working with spherical videos, because since we have an entire 360-degree view for the spherical video. So there are 4 phases for any kind of spherical video summarization. So one is recording phase, and another is the processing phase, and the third is the stitching phase, followed by the visualization phase. So what is the recording phase? The name itself tells us. A spherical camera is being used. From that spherical camera, a spherical surveillance video. So I guess the term surveillance is very familiar with everyone. So surveillance is something which keeps an eye, or we can say that monitoring something on the area where it is being focused. So by using a spherical camera, the region is being recorded. So here you can see the sphere balls, the balls kind of frames. So the difference of non-spherical video and a spherical video. In a non-spherical video means the traditional video, what we are using in our day-to-day life. It has a frame in which is of rectangle shape. But in spherical video, the frames are in sphere, which is spherical. So now in the processing phase, we have object detection. After object detection, interaction preservation, object track extraction, spherical background extraction. So what are all these? I'll discuss in detail in the next coming slide. Just I want to focus more on this figure. So in stitching, we are trying to stitch the object tube rearrangement and the objects to the background. In visualization phase, this happens once the generation is over. So the first three phases deals with the generation of video synopsis, and the last phase deals with the visualization or how we are going to view the generated video. So the first approach, what we have seen is, we can see a direction based visualization. So moving further in detail, recording phase. So in the recording phase, what I do is, we will use a spherical camera. With that spherical camera, I'll be trying to cover, or I'll be trying to record the entire region of that particular area. So now let us assume, or let me say that R denotes the input spherical surveillance video recorded by using a consumer based spherical camera built. So what do I mean by spherical camera? Means a spherical camera is something which contains multiple traditional cameras inside it, which is directing towards all the four directions. So ultimately, when all the four directions are independently recorded, this spherical camera will stitch them together to give us a 360-degree view. So once the recorded scenes are stitched together to create a spherical frame. So I'll repeat again. What a spherical camera is? A spherical camera is an hardware device which contains multiple traditional non-spherical cameras inside it, so that each non-traditional traditional cameras can record the scene independently and ultimately stitch them together to give an entire spherical view of the frame. So this is the recorded spherical video frame in equirectangular projection. So why should I give in an equirectangular projection is to make it, what I'm doing here is, I'm trying to, my spherical frame, I'm trying to stretch it over just like my traditional video. So here you can see, so this part and this part, when you bring it together, it will become a sphere. So just for the normal traditional view, I have just cut in the middle of the spherical frame and made it projected into an equirectangular projections. So if this part and this part is folded together, it becomes a spherical view. So now the next one is the processing phase. So what is happening in the processing phases? As we have seen in the figure, we have four process that is taking place. So first and the foremost is the object detection. So let us assume there is a spherical camera which is focusing on the road. So what am I interested in that spherical video? The activities which is involved in that particular video. Who is doing the activity? Objects. For example, person. The person who is walking in that particular road is doing some activity. So how can I do that thing is object detection. So once the objects are detected, what I can do, I can try to identify which object is performing an important or suspicious activity. So let us say a person is walking for a particular number of time, time, and after that time, he is running fast, which is an abnormal activity. So how do we find these abnormal activities? The initial and the foremost step is nothing but object detection. So how can I do this object detection? There are various deep learning approaches, deep learning techniques, which provide better result based on the particular applications. So one such technique, what we used is a fast region based convolutional neural network, which which detects the objects in the surveillance video and store all the objects in a data structure called object queue. Now, moving on to the next process. Once I have detected objects, now while detecting the object, there is also one more challenge which involves interaction. For example, let us say a person A is coming, we are focusing on a road where a person is coming from left to right direction, and the other person, opposite some person is coming from right to left direction. So now what happens at a particular time, the two persons to the two individuals are known to each other. So they are trying to give an handshake. So what is happening in this time? The camera records handshaking. So when you do object detection, such kinds of interaction should be preserved. So what we should do, we should not detect that particular moment as object A, object B. Instead of considering them as an individual object, for that particular time, we should assume them as one single object. That is, that handshake should be preserved. So how can this be done? A recursive tube grouping algorithm, which was proposed by Namita et al. There they discussed more in detail about why this interaction should be preserved. So using those technique, we can try to preserve the interactions between the object while doing object detection. So now object detection is done. If there is any interaction, that is also preserved. So what do I mean by the term object detection? For one particular frame, where is the object? What is the object? Is the object having interaction? So the first two things deals with frame. Now I am moving into a video track extraction. From the first frame to the end of the video, where all these objects are coming, a particular object, let us say I have detected 3 objects, object A, object B, object C. Now I have detected them in one single frame of a video, surveillance video. Now I should know in what time or in what all the frames these 3 objects occurs. So now what I'm going to do, I'm going to extract the track of the object. So what do I mean by extracting the track? From the start frame to the end frame, the object A has occurred in what all number of frames. It can be in frame 1 to frame 100. The second object can occur from frame 1 to frame number 50. The third object can occur from frame 1 to frame 20. So this is known as object track extraction. So deep, simple, online, real-time tracking approach. So there are various object tracking algorithms. Any of them which suits the application best can be used to extract those kind of object track extraction. So the fourth process in the processing phase is spherical background extraction. Once we have recorded, detected and extracted the track, we should know the background scene. For example, if the surveillance camera is recording the road, what will be the background? The plain road with no objects. So this processing phase, at the end, what it does is, I will detect the object separately. If there is an interaction in the object, that will be identified. I'll be trying to find where all the objects are having from the start frame to the end frame, and finally I will try to extract a video which has no objects, only the background. So why do I take this background information? You will know that in the next phase, stitching phase. So this is the illustration for processing phase, where you can see the object detection, what are the objects that are involved or identified, and next is the interaction preservation. In interaction preservation, you can see the two people who are interacting, so that can be considered as one unit, and that will be preserved in the output video. Now a track of 12 objects. So now in this video, I had 12 objects. So these are the areas where the particular, this is object 1, object 2, object 3. So like this 12 tracks are given. So from the start of the video to the end of the video, where are these object has the movement of the object that is happened in this video is extracted using the track extraction. Now this is something which is known as background extraction. So background extraction is something which is not having any of the objects in it. So why do we need this background? We will see in the next phase. So that is known as stitching phase. What is the stitching phase? Now in my hand, I have all the objects that are occurred in the input video. Now what I should do, I should come up with an optimization technique which tries to put the objects in such a way that at the end I am able to see a shorter representation of the video. So that is known as stitching phase. So in stitching phase, object tube rearrangement takes place. The synopsis video is generated by minimizing the subsequent video energy cost function. That is, it minimizes the energy synopsis. One second. So there is one picture which represents the video summarization. So I think that the picture is not available here. So what is that video summarization is, we will be trying to showcase all the events that is being worked in there. So now minimize E of S is nothing but the activity cost, collision cost, temporal consistency cost, length cost, and frame packing cost. So what is this? What is these cost value is? First, we have objects, detected objects with us. Now, with this object, how to create a synopsis video in an effective way is to work with all these costs. So what is all these costs? We will talk about them. Before going into what these each cost is, I want to stress about the weight that is being given. So this beta 1, beta 2, beta 3, beta 4, beta 5 are the weights that are given to the particular cost function. So here if you see, beta 2 takes 0.4. Collision is given higher preference than all the other. So why this collision is given higher preference? First we will start with what is activity cost. So the point to be observed or inferred from this slide is collision is given high preference. Why it is given high preference, I'll tell you when I talk about collision cost. So first starting with activity cost. So activity cost means, what is activity cost means, when I try to create an synopsis video, let us say from 3 hours movie, I am trying to create an half an hour just a short synopsis of that particular movie. Let us say the movie name is A. From the movie A, I want to create a 30 minutes synopsis of that movie. Means I should make sure that I'm not missing any of the activity that happened in the 3 hours movie. So that is taken care by the activity cost. So it penalizes for losing any activity during the temporal mapping from the input video, from my 3 hours movie to this 30 minutes synopsis movie. Okay, so the input is my 3 hours input, 3 hours movie. Let us say movie A. The movie name is A. Let us say it is a movie. Now, from this movie, I'm trying to create a short synopsis of that movie. A means the activity cost makes sure that there is no missing of any characters that is involved in that 3 hours movie. Same characters are also available in this synopsis movie. So that is taken care by the activity cost. Now moving into collision cost. So what is this collision cost? I'll try to recall. I would recall that this was the most weightage which is given in an optimization algorithm. Why is it so? So when I see a 3 hours movie, I was able to spend 3 hours to understand what is the scene in the movie, who are the characters, what is the theme of the movie, and what is the climax of the movie. So I'll be trying to try to get all these information. But same 3 hours movie, when I try to shorten it into 30 minutes of a synopsis movie, what is happening? The characters are put together in the sense each frame is stuffed with objects, lots of objects. So ultimately what happens is collision can happen. The characters, let us say there are some n number of characters. The character number 1 and the character number to in the synopsis, that is the original video. In the movie, they are not meeting each other, but in this 30 minutes, we are stuffing the objects together. There may be a chance that they collide with each other. So what is the possible solution for that? We give higher preference for importance for this particular cost function, so that the synopsis 30 minutes movie video is generated in such a way that no two objects collide with each other. So that particular optimization algorithm will try to minimize the main goal is minimize. So minimize all these aspects. So activity cost we have seen, second one was the quality cost, and the third one was temporal consistency cost. What do I mean by temporal consistency cost? Means the same example in the movie, the character which appeared first, for example, let us say the main character of that particular movie has appeared first. Next comes the supporting characters. Same order should be preserved in the 30 minutes of the synopsis movie also. The main character only will appear first, then the supporting characters. So that order should not be changed. So this is taken care by the optimization algorithm. What is length cost? As I have told you, 3 hours movie is shortened into 30 minutes. So always it should keep an eye on 30 minutes. It should create only within 30 minutes, not more than 30. So the length of the output video is taken care by this length cost function. The final and the foremost one, the main objective of this work is frame packing cost. As I have told you, a viewer can view. For example, let us say you are watching a picture. Let us say a picture of a movie. Picture means a photo of a movie. Let us say the post of a particular movie. So what the information can be gained only if the poster of the movie contains very important characters in that particular poster. If we try to stuff all the characters, let us assume a movie is containing some 12 to 15 characters involved in that movie. If I try to bring in one movie poster all the 15 characters face, then what happens? The information that is to be gained or the importance of that particular poster is lost. So what is the possible solution for that? I am trying to limit the number of objects that should be visible in one particular frame. So what I do for that particular movie, I'll create a poster or I'll have a frame where I have only the main characters of the movie. Let us say there is only 3 people or the 3 characters who are really important for that movie. Then only those 3 will be kept in that poster. So ultimately, what is happening here? The information gained by viewing a frame with 12 characters or 12 objects is less important compared with the poster or frame with having objects of only 3 characters. So what happens? As you limit the number of objects to be displayed per frame, the information that is gained for the viewer or the person who is viewing that movie or the synopsis video can gain more information. So the optimization techniques perform all these things to make sure that at the end we are able to get a synopsis video of 30 minutes which keeps an eye on all these 5 parameters. So now once the optimization algorithm is used, it will give us a best possible solution where each characters can be placed in each frame. Now what I do, I will take up this answer and I'll try to attach or I'll try to stitch the object with a background image. So that is the stitching phase. According to the best temporal solution obtained, the objects and the respective timestamp from the OQ. What is this OQ? The objects stored in the object queue. Detected objects that is stored in the object queue are taken and stitched to the spherical background using the Poisson image editing mechanism. So now, so far we have touched recording phase, processing phase, and stitching phase. So with these 3 phases, the generation of 30 minutes of synopsis movie is generated. Now, how do I view the spherical synopsis video is, I can view by using first saliency detection. What is the saliency detection is, in my synopsis video, I am trying to find the regions where there are salient features that happen in my video. So for
Did you?
hello, sir.
Yes, madam.
Sir, now am I audible?
Yes, madam. It is clear, madam.
Okay, sir. May I proceed, sir?
Yes, madam. You can continue.
Okay, sir. Okay.
Ma'am, give some time, madam. I'll make you a co-host. Then only you can
Ah,
share the
okay,
screen,
okay, 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 sir. Okay.
Ma'am, now you can share
Now
the
you can
screen,
share,
ma'am.
madam.
Okay, sir. Okay.
Okay, okay.
Sir, now is my screen visible?
Yes, ma'am. Yes, yes.
Okay, okay, sir. Okay. I'll proceed with this.
Okay.
Okay, sir. Thank you. So now, so this is the area, the thing which we were discussing. So, saliency detection, where the important events are identified. So now, what is the next one is? Now after the synopsis video is generated, now the idea is visualization, how we are going to visualize them. So when we visualize the video, what we try to do is we have to do a projection, which is a spherical video representation into a normal traditional view. So what is the projection named is genomic projection. So what does this genomic projection means? It maps the equirectangular projection onto a rectilinear projection. So what is this rectilinear projection is? A projection which is viewed as a normal field of view. So it displays the interested field of view of the spherical image where the human perceives the world with an undistorted way. So if you see here in the spherical video, all the images, all the pixels will be in distorted form. Okay, so now when you convert into a genomic projection, what is happening is we are able to view a straight line. What I mean is a line will be curved in the spherical representation, whereas through this genomic projection, we will be able to convert it into a normal projection. So this is the step of procedures which are involved in the genomic projection. So I'm not going much into the genomic projections procedures. This is the goal. The goal is to convert the view, a particular view, interested area of region into a normal traditional view. So once that conversion is done, my output generated spherical synopsis video can be converted, visualized direction based. So direction based, how I can view is my left region, what is the activity that is involved, in the front region of the video, what is the activity that is involved, in the right region, what is the activity involved, and finally, what is the activity that is happening at the rear end. So now the next one is I'll be just telling what is the algorithms, and we'll move on to the next approach. So various optimization algorithms are used to identify which one performs better. So on that aspect, we just collected few optimization algorithms which was already used in the video summarization approach and which was not used. So in that case, what we found is we found different algorithm gave different results. So the experiment was started with a real-time surveillance video, which was recorded with 24 frames per second with a consumer 360-degree camera, which has 20 interacting objects, and this is the resolution. And the MATLAB was used with the program was for 100 iteration with 10 number of populations. So now we experimented in two ways. One is varying synopsis length, and the other is predefined synopsis length. So what do I mean by varying and predefined is, let us say the 3 hours movie video can be converted into a shorter synopsis movie video within 30 minutes, or I can convert the 3 hours movie video into any number, any minutes, or any count of synopsis video. It may go to 1 hour or it may go to 45 minutes, any hour. That is known as predefined and varying. In predefined, there is a limit for the time. This is the time within which I want to finish my video synopsis. Whereas in the varying synopsis length, there is no difference. There is no times, no such time limit. So now I will just go through once. I will just tell you what is the process that has happened with the optimization algorithm in terms of each cost function. Collision, for the collision cost, we can see the graph here, and I have denoted the optimization algorithm which performed better. So same goes for temporal consistency, length cost. We can see particle swarm optimization algorithm gave better result. Then frame packing cost function, the other two optimization algorithms for both varying and varying as well as the this one predefined, how it is going. So same way, convergence characteristics, which optimization has converged well. So and-line optimizer and particle swarm for varying, and and-line optimizer for predefined length. So talking about the performance metrics, how can I get the performance metrics of the synopsis video is, I'll try to find what is the object loss, what is the activity preserved. That is, from the 3 hours movie, have I covered all the characters inside the synopsis video? What is the space efficiency? How much is the space efficiency by comparing with the input video as well as my synopsis movie video? chronological disorder. The character which has occurred in an order in the movie, it's the same order they are occurring. If the main character has occurred first in the movie, then my synopsis movie video should also contain the main character first. Like that, it has to maintain the order. Next is overall visual cohesion. Is there is any colliding between the characters of the main movie that is preserved in the generated synopsis movie, or is there any unnecessary collisions which has to be taken care? So these are the performance metrics. Now, on that basis, we saw the performance of each algorithm. So you can see the red highlighted ones or the better ones compared with the other one. So same goes with the object loss and activity preservation rate. Then how we focused our analysis is for the given time period, what is the number of objects that it is that the particular video is containing. So for 4 minutes, how the activity preservation and object losses. So these are the experimental part. So in the first work, a summary of this is we generated a synopsis video and then we tried to see the direction based visualization. We also try to restrict the number of objects to be packed. Then we focus more on the analysis part. Now, when we come to the second way, in the second way, the problem of viewing 4 based direction. Why should a viewer should focus on all 4 direction? Instead of focusing on all the 4 direction, we made it an customized approach. What is this customized approach is? He can be a center point of viewer. Wherever he want, only that area of interest he can be able to view. One more thing what we included in this one is an action recognition. So either go for action recognition based on the user or directly go for stitching and then visualization phase. So the main thing is action recognition. What do I mean by action recognition? When there is an abnormal behavior of an object during a surveillance video, it has to be correctly identified and same information should be contained in the synopsis video. For example, if you see the highlights of a cricket match, what is the highlights of a cricket match? It provides the main event that has happened in some 3 to 4 or 5 hours of cricket match. So the 5 hours of cricket match is being shortened to 15 minutes of in terms of highlights. So what is happening there? The key events are identified. They are given prioritization, and based on that, a short cricket highlights is being provided within a specified duration. So that is done by using this prioritization mechanism. So this is how the processing phase can be done. So when I talk about my objective function for optimization, it includes the action recognition, which gives the priority score. So one more thing to be identified in here is minus. So I'm trying to maximize the activity that are involved in the synopsis video. For example, if there is a running event, if you see in a road is being it is surveillanced for a particular duration. If an object is running, it should be given more preference than the object which is walking. So the first and the foremost priority is always given for the actions which are having an abnormal behavior. So that is known as action recognition. So this is the main cost function for action priority cost. And stitching. In stitching, what is happening is the objects are identified same as that of the previous discussion. So the main focus is visualization. Instead of going a 4 direction visualization, which is what I'm talking about is this one. Instead of individually focusing on left side what is happening, front side what is happening, right side what is happening, at the rear end what is happening, we are trying to provide a customized visualization where the viewer will be at the center point. He will try to view only the interested area. So what it reduces the boredom of viewing a fixed field of view, whether it is left, right, or back. So this is one example for customized visualization, where you can see wherever I want, I can change my field of view, top, bottom, anywhere I can see. So here also we used few optimization algorithms. So these are the experimental part, and just why I'm focusing on these experimental part, we are just seeing once this to see the red highlighted parts, which shows the better optimization algorithm, because our ultimate end, we are going to propose an optimization algorithm. So the performance metrics, which is same as the other. In addition to that, we will also make use of frame condensation ratio and important action. How many percentage of important actions are included in the synopsis video? For example, from the movie, what are the important actions, whether that important actions are included in my 30 minutes of synopsis movie video or not. So same is the performance metrics for the algorithms are done for different varied length as well as the predefined length, with action and without action. So these are the experimental parts of how the optimization algorithm is performing. So the summary of this is, we introduced an action recognition into the surveillance video synopsis framework. And also we proposed that don't see a fixed field of view, whether it is left, right, or back. It creates a boredom. So make it dynamic. How to make it dynamic? Keep the viewer the center point and change your field of view, your yaw angle and pitch angle in the generated synopsis video, so that you can generate a dynamic visualization of the video. So this is the solution for the previous one. Now, moving into the spatio-temporal summarization. What is the spatio-temporal summarization? If you see the first two cases, we were only trying to reduce the length of the video. The 3 hours video is converted into a 30 minutes synopsis movie. So now what we are doing in this spatio-temporal is, we are trying to reduce both in terms of space as well as time. So here you can see, wherever the person is viewing, only that region the objects are taken and they are optimized, and then we are trying to view them. So for that, we perform object tracking in the processing phase, then we do viewport prediction, and then we do personalized cube rearrangement, and then finally we go for visualization phase. So what we are doing is, this is just a representation or then illustration of what is happening in a spherical video. This end and this end, if you join together, it will be a sphere. So what I do, I partition the spherical frame into 4 regions and try to group the objects that occur in these partitions. Partition 1, partition 2, partition 3, and partition 4. So whenever the object is viewing in this partition 4, I will only access this object, tube T5, and I'll try to extract them, perform optimization, and then I'll try to generate the synopsis video for this one. So this is an algorithm which takes whatever I have told now is the algorithmic representation. And now I do viewport prediction. What is this viewport prediction is, I use long short-term memory for a particular time. This is the movement of the viewer. What will be the movement for the next coming frames? So you can see here, I predicted view angle and pitch angle. What will be the future views that the particular viewer will be viewing? With this information, I will try to find whether the previous, if you see this viewport 1 and viewport 2, you can see their collision is very less. So here, if you see 3 and 4, the collision is more. So what I will do, I will not take these predicted viewports 3 and 4, because if there is more percentage of collision, then I am accessing the same objects. So that condition is avoided. What I do, I take the viewports only if they have less than 10% in both yaw and pitch angle. So what happened? My object which I'm trying to take will be having a more more content, or the more objects I will be. So in this case, if you see, I will consider only this part till here T5, and the remaining is considered in this viewport. And here, if you see, the same object is being considered multiple times, the 2 times. So this kind of case is avoided. Only this kind of cases of viewport prediction will be obtained. Now, after predicting the viewport, the objects within them are selected dynamically, and then optimization process will take place, which is same as the cost function, which we have already discussed. Based on that, we'll be trying to stitch the objects to the background which is being extracted. So this is known as personalized object extraction. So what is happening here, which is different from the other two approaches what we have discussed, is in other approaches, objects are detected, interaction is preserved. Once optimization is done, I'm sticking it to the background. But in this work, what is this being done is, I am trying to find the viewport, future viewport. Once my viewport is identified, I identify what is the objects that lie in that viewport. Only for that objects that lie in that viewport will be performing optimization. And once the optimization is done, I'll be trying to generate a synopsis video for that. So for this, we used the same, like we worked on few optimization algorithms, and at the end, we came to know that the simulated annealing gives a better result with compared to all the so far discussed optimization algorithms. So the summary of this one is, we were able to generate a personalized video synopsis framework, which is different from the discussed previous two works. So here we introduced object grouping also. By doing this object grouping, we are able to generate a dynamically generated one. And in terms of observation, we observed that Aquila optimizer minimizes the collision effect. When you try to shift the objects, it try to reduce the collision, and then it provides better results in other cost functions also. With this information, when we move on to the next one, we introduced an optimization algorithm, multi-objective hybridized Aquila with simulated annealing. So this is one optimization algorithm which gave us a better result to generate a dynamic synopsis video. So here what we did, we introduced an optimization algorithm with the same process which happened in the previous case, just to make it a little more optimized one. So the algorithm contains 4 stages: expanded exploration, narrowed exploration, expanded exploitation, and narrowed exploitation. So the key things is, what we do is, we try to boost the Aquila optimizer with the simulated annealing approach. So how this? So these are the things which is normally happening in the Aquila optimizer, where the eagle is the background information is taken from how the eagle is able to hunt its prey. What are the stages it goes through in hunting its prey? If you try to see in application ways, how we are able to reach to a goal, an optimal goal. So that is eagle, how it is reaching its prey. So these things are the normal explanation of the process, Aquila optimizer, simulated annealing, where we will be able to, it is a state where we are allowing the process, or allowing the application to reach to a global state, global minimum state. So these both are merged together to generate and to introduce an optimization algorithm, multi-objective hybridized Aquila with simulated annealing optimization algorithm. So what we propose here is a Pareto optimal. Instead of doing a weighted sum in the previous approaches, what we do, we create an Pareto based approach. What we do is both minimization and maximization. What should be maximized? The action that is involved should be maximized. What should be minimized? Activity cost, collision cost, temporal consistency, length cost, and frame packing cost should be minimized. So this is the proposed algorithm. What we do is, in the 4 stages of Aquila optimizer, we are trying to inject a probabilistic selection of selecting the global output or global answer for creating a video synopsis in all these cases, along with the characteristics of the simulated annealing approach. So we used, in the previous 3 approaches, we used only one video. In the other, in this work, we have worked on different videos as well, like these three videos taken at different time locations. we try to analyze the performance of the optimization algorithm. So here you can see it is of Pareto optimal based, where minimization as well as maximization. Minimization of all the cost function and maximization of all the actions that are being involved in the input video is identified. So for all the video 1, video 2, and video 3 is being analyzed using the introduced optimization algorithm. So we went on to see how the algorithm works for different videos in comparison with other algorithms. In all the cases, we found there was a better result which was fetched from the introduced multi-objective hybridized optimization algorithm. We also saw for a given time period, if I see for 3 minutes, what is the count of important actions involved? For 6 minutes of the synopsis video, what is the important action percentage? So in all cases, we were able to achieve a better result compared with that of the existing optimization algorithm. The same table is illustrated in a pictorial graph form for all the video 1, video 2, and video 3. So the summary of the last one is we were able to generate a personalized video using an introduced hybridized algorithm. Why actually, what is the main aim to go introduce this is the Aquila optimization has a trapping problem. So this because of this trapping problem, we will not be able to go to a global solution. So that is why we introduce a probabilistic selection from the annealing approach. So with this, we were able to generate a better video synopsis for the particular. So that is about the recap. So one thing which has to be discussed from the first one is there is a video summarization picture which has all the information which the same thing which we have discussed. So here if we see all the input images for all the input activities which are involved is being you can see the frame by frame video summarization. What I'm showing right now is a non-spherical video. You can see all the activities in the input recorded surveillance video is condensed into a shorter video by stuffing the objects in such a way that they do not collide with each other. So this is what the figure right now, what we are seeing is the video summarization, where the input video is condensed into a short video. And this is an example for non-spherical video. So for whatever I discussed was about the spherical video. So if we see the recap of whatever have been discussed for this session is, I was talking more about spherical surveillance video synopsis framework, where I discussed more about the 4 phases: the recording phase, processing phase, stitching phase, and visualization phase. Once the generation is done, how am I going to view the spherical generated video? Because I have 360-degree view. One approach is I can go direction-based approach of visualization. What do I mean by direction-based approach? I can view individually front region, what is happening, left, back, and so that I can cover all the 360 regions. One more thing, what we observed is, let me limit the number of objects to be displayed per frame. What is the intention behind that? The viewer will be able to understand the scene in a very effective way. Then we moved on seeing that actions are really important in a surveillance video. So why do I go for action recognition? So that I will be able to identify the normal behavior as well as the abnormal behavior. So I should know the difference between the normal behavior and abnormal behavior. That is the reason why we introduced action recognition also. We also saw the performance of all the algorithm in terms of varying as well as predefined. What do I say by varying and predefined? In my case, let us say I'm having an input video of 3 hours movie. Now this 3 hours movie can be converted into a video synopsis with 30 minutes as a constraint, or there is no constraint. So that is known as varying length or predefined synopsis length. And then we moved on to see what is personalized video synopsis. When I see in a fixed direction, like 4 direction. I'm forced to see in only that particular direction. I don't want my viewer to restrict to a particular direction. So I came up with a customized visualization. What do I mean by customized visualization? Once I generated my 360 degrees synopsis video, I want to view only the regions where I am trying to view. Now, what I do is, after knowing this information, I am trying to move on to an area where I will propose an algorithm or an object track grouping mechanism, dynamic mechanism, where I will not generate video synopsis for all the objects. I will identify the field of view, interested view, using the viewport prediction, long short-term memory. With that, I will predict my future viewports. With that viewport, I'll try to create a video synopsis only for that region. Now, when I come up with this solution, what is the best optimization algorithm that I can use? From the analysis what I have done, it is seen that Aquila gives better result, but it has the ability to get trapped in local optima. So what can be the possible solution is, I am including a probabilistic selection into the Aquila so that it provides a better result. So by this way, these are the approaches how we can create a video summarization for the spherical videos that can be recorded. So these are the references which I have used for this particular session. Thank you for having this session. Hello, sir. Am I audible?
Yes, ma'am. Yes, ma'am.
By this, I conclude this session, sir.
Yeah. Okay. So yeah, thank you so much, ma'am, for your informative talk on video summarization.
Thank you, sir.
Santosh, sir. Yeah.
Yes, sir.
Yeah.
Thank you, madam.
Thank you, sir. Thank you so much for this opportunity, giving this opportunity, sir. I thank all the participants also for having this session with me. Thank you, sir.
Thank you.
Thank you.
Thank you, sir.
We will stop here, madam.
Yes, sir. Yes, sir. So I will stop here. Thank you, sir. Thank you.
Yes.
Dear participants, our day 3 sessions conclude here. So we'll meet on tomorrow, day 4 sessions. Okay. Thank you on and off.